Hi, hi, hi. Okay, this is part one of two. So I'm doing the first video just on neurophysiology, and then and I'm probably focusing a little bit more on anatomy than y'all need for your NBME. But I do find that it's helpful to understand like the geography and landscape of the brain, to understand strokes and tumors and the effects that they'll have on proximal tissue. The second video is going to be more on pathology, and that's probably a little bit higher yield for your NBME. But again, I think if you have a nice foundation with this first video with the neuro, then the pathology comes a little bit easier. Okay, let's get in. All right, so we're going to start with like a big picture overview, talking about the cerebral cortex, introduction to subcortical structures, and then we're going to go into more depth on each of these. Basal ganglia and dopaminergic pathways, limbic system, thalamus, hypothalamus, pituitary axis, the cranial nerves, the brainstem, cerebellum. We're kind of moving like, superior to inferior as well, if that makes sense. Going into the spinal cord. Then we'll talk about the vasculature, which is really high yield to understand strokes, the meninges, the ventricular system, and then the venous drainage, which the three of these kind of go together. And then just a couple things about cell types and the peripheral nervous system and embryology. All right, so a lot of people it's fun, colloquial, conventional science to talk about the triumvirate brain, right? Where like the bottom part of the brain is the reptile, and then we have the limbic system, which is, the mammalian brain, and then the neocortex is all of the complex thinking. And I don't know, maybe there's like a shred of truth to this, and it's fun to talk about just in like dumb bar conversations, but the brain, obviously, as we're going to go through, doesn't really work so much like this. Similarly, people kind of overhype the differences between like the left brain and the right brain. The left brain is so rigid and mathematical, and the right brain is all artistic. Again, probably some shred of truth, and I'm definitely not the guy to really answer that debate. But again, I think it's overblown. What you should know is the left brain typically controls the right muscles. The right brain typically controls the left muscles. There will be exceptions. The language center is typically, but not always, on the left side of the brain. And just to really highlight, like, you can have a hemispherectomy. You can take out one entire lobe of the brain and you're still fine. The truth resists simplicity, right? Like we've talked about the triumvirate brain, the left versus right brain. So a lot of the borders that we're going to see are going to be fuzzy, right? So when we say, oh, the parietal lobe is for touching, well, the other parts of the brain are also going to have a role in touching as well. It's just that the right part of the parietal brain might play a larger role in touching than other things, et cetera. All right, so let's get in. Here's the brain. Let's do it. I made a bunch of dumb videos, so we're going to have to suffer through them. Okay, so the calvaria are the parts of the skull that border the brain, and that's where the cortex of the brain is named after. So here we're looking at the frontal bone covering the frontal cortex, and then you'd have the parietal bone covering the parietal cortex, etc. Those are calvaria. All right, so we open it up. We have two dural layers, a cranial dural layer, and then an intermeningeal dural layer. That's important. Then the arachnoid layer, and then the pia matter of the meninges, which is not shown. So let's go below the cortex, looking at all the subcortical structures under the cortex. We have the falx cerebrae, which we'll talk about. It's a dural layer. The corpus callosum, left and right communication, the lateral ventricle. Here we have the basal ganglia with the caudate nucleus and the putamen. Then the tutorium, which is also part of the dural layer, very similar to the falx cerebrae, and it's going to we're going to have subtentorial and supratentorial structures. It's a way that commonly we will talk about the geography of the brain. Okay, so the cerebrum really just means the cerebral cortex plus the basal ganglia and parts of the limbic system, which is there's not as much unity in the limbic system as there is compared to the basal ganglia. Here in the back, we have the little brain, the cerebellum, and then of course the spinal cord and the brainstem, and these gyri and sulci, which we can talk more about right now. So yeah, we've got a left hemisphere or left hemisphere and right hemisphere. So the sulci and the gyri, I would just think of them as like a mountain and valleys, right? So the valleys is going to be the sulcus, and then the mountains on either side are going to be the gyrus. Then the periphery of the brain, we have the gray matter. That's where the axon body, the somas, the neuron bodies are going to be. And then the white matter is where the axons are. You can see a picture here a little bit better. And this kind of makes sense if we imagine that everything's going through the spinal cord, through the brainstem, and it's trying to make its way to the periphery where these, headquarters cells are. It would make sense, in my opinion, to have the soma, the cell body on the outside. Notice that, though, this is the opposite of what we see when we're looking at the spinal column. Here we're going to have the gray matter, the cell bodies on the inside, and the white matter on the outside. So the frontal lobe is going to be for complex thought, emotion, and motor function. We have a density of motor function in the somatosensory cortex of the frontal lobe. Parietal lobe is for feeling and touching, and we're going to have a density of feeling, touching neurons in the somatosensory cortex, which borders the somatomotor cortex. Occipital lobe is going to be for vision. Temporal lobe is going to be for hearing, a little bit of emotion, a little bit of limbic system. We have this Sylvian fissure right there. That's going to be important to separate the frontal lobe from the temporal lobe. And then we're going to have the Sylvian fissure is also known as the lateral fissure. And then we have the central sulcus, which is going to separate the frontal lobe, parietal lobe, more specifically the somatomotor cortex from the somatosensory cortex. All right, so I recorded these and I didn't realize I had the sound on. So you guys are going to, if it wasn't evident what a nerd I am, you're going to hear the music that I listen to on Spotify while I'm doing this. So this is just a video showing the Sylvian fissures, lateral fissures, and then the central fissure. Cool, epic. All right, so most people are right-handed, 90% of the population. And if you're right-handed, again, we said that there's this kind of like, right-handed people goes to the left part of the brain. So if you're right-handed, your left brain is dominant. And so then the language center will be on 95% of right-handed people. Now, if you're left-handed, that means that your right brain is dominant. But it's weird that, again, even if you're left-handed, the right brain is dominant, you still typically have the language center. So for left-handed people, 70% of people are still going to have the language center on the left side. Again, that's really important for Broca's area, which is kind of for like speech production, and then Wernicke's area, which is for like speech comprehension. So when in doubt, it's just safe to say that the language center will be on the left side. All right, so we're going to listen to Broca's aphasia here on the left, known as non-fluent aphasia, because they can't speak fluently, but there is meaning behind what they're saying, as opposed to Wernicke's, which we're going to hear on the right, where people can talk fluently, hence fluent aphasia. They can speak and say all they want, but not a lot of like content is really coming out. So let's go ahead and listen to this guy on the left. He's talking about how he had a stroke and he started a support group and the amount of people he has in the group. So let's take a listen.
Founder for me, and members.
Notice how hard they're struggling to find the words.
How
long it takes.
Members, probably 60 people.
So 60 people are part of Voices of Hope.
Yeah.
Okay, let's listen now to Wernicke's aphasia and just notice the contrast.
Hi, Byron. How are you?
I'm happy. Are you pretty? You look good.
What are you doing today?
We stayed with the water over here at the moment and talked with the people for them over there. They're diving for them at the moment. They'll save in the moment. He'll have water very soon for him. With luck for him.
So notice that like the words per minute in Wernicke's aphasia is not so different than it would be for someone who hasn't suffered a stroke, but the content, the meaning is a little bit lost, right? There's some meaning you can connect. He's on a cruise and people are swimming and they're happy, and like you can, and maybe the girl's pretty he's talking to, but like it's not as sensible as a Broca's aphasia. All right, we're gonna hear more dumb music. So this is just showing the difference between the precentral and postcentral. Precentral in the front, and postcentral on the back. Okay, so when we're looking at the precentral and postcentral, again, divided by the central sulcus, we have this homunculus, where things kind of in the medial side are going to be more like your legs, and then things on the lateral side over here are going to be more for the face and the upper arm extremities. This is going to be really important when we're doing ACA versus MCA strokes in the future. So the homunculus, you have more nerves dedicated to things like your hands and your lips, and that makes sense. You got to feel where you're going. You have to differentiate like a sharp object versus like a smooth object, and same with your lips. Something hot is something cold, is something poisonous, etc. And then maybe something like your left oblique doesn't really need as much like high octane like sensory differentiation. And so, yeah, we're going to, feeling, you can read Braille, you can eat ice cream, you can differentiate. And so if your, homunculus is functioning, you should be able to feel things. And if it's not functioning, you have an ACA or an MCA stroke, you're not going to be able to touch or feel or move muscles or and whatnot. Moving down into subcortical terrain, Again, we have the falx cerebri, we have the tentorium cerebelli, we have the corpus callosum, we have the ventricles, we have the basal ganglia. Here you can see a little bit of the hippocampus and the amygdala. An important distinction here, again, geographic term, supratentorial. So we just saw the, down here, the tentorium cerebelli. Things above this are supratentorial and things below this are infratentorial. This is just a natural invagination folding of the brain, which is really hugged tightly and strongly demarcated by the meningeal dura. And so anything above is going to be supratentorial, anything below is going to be infratentorial, largely, again, to separate the cerebrum from the cerebellum. So a couple things we're going to be going through now are going to be some subcortical, so that is to say below the frontal lobe, temporal lobe, parietal lobe, occipital lobe, but supratentorial, so above that tentorium cerebelli. This includes the corpus callosum, the lateral ventricles, just 1 and 2. We have ventricles 3 and 4, which are going to descend down infratentorially. The basal ganglia, which is several different structures. Limbic system, which is several different structures. Also very arguable. People debate about, what is the, cohesiveness of the limbic system. The thalamus, largely a relay station, and the hypothalamus pituitary axis. So the corpus callosum is just going to communicate the sort of left and right side of the brain. You can see it here. You can see it very clearly here, connecting the right side here with the left side. We can see it here. So it's basically the most superficial aspect of the brain, apart from the cerebral cortex. And again, you can see it here as well after we've sort of taken out the cerebral cortex from our picture. So 1981 Nobel Prize, this is kind of amazing. People who have severe epilepsy, to prevent the spreading of electrical signals like wildfire throughout the brain, they cut the corpus callosum so that it can't spread as much, and this kind of stops it. But that means information can't be shared between the left and the right. And again, remember that when in doubt, left part of the brain has to do with right sensory system and right motor skills, and then vice versa with the other side. So here's a person, they've had their corpus callosum severed. They see the word face. It's on the right side of the visual field, which means it goes to the left part of the visual brain. We said that the language center is on the left side. So somebody says, hey, what do you see written? And that is in the left part of the the left part of the brain, that information. And they can speak with the left part of the visual brain. So they go, I see the word face. Okay, well, let's put this now in the left part of the visual field. That goes to the right part of the brain. Now, though, that information, that the word they see as face, cannot cross to the left part of the brain because the corpus callosum is severed. So if they need to communicate that with verbal speech on the left side of the brain, well, the left side of the brain doesn't know what we're seeing, right? You and I take for granted that there's a sharing of information between the corpus callosum. So they will say, I don't see anything, because again, there's this separateness of the left and right hemisphere. But the writing skills are intact just on the right part of the brain. So they say, I don't say anything. That's the left brain being unaware because it can't communicate with the right brain. But the right brain can control the left arm to write that they see a face. Kind of amazing. The lateral ventricle, so we have this whole ventricular system. These are just the lateral ventricles. They kind of look like the horns of a ram. And the ventricles are going to play a role in the generation and flow of cerebrospinal fluid, which provides nutrients and takes away waste. Kind of like water coming to the house, right? Water coming is nutrients, taking away sewage is taking away, things that we don't want the output. And it's going to have a complex drainage where the cerebrospinal fluid will ultimately drain into the venous system to get out of our head. So three very important systems really are the basal ganglia, limbic system, and the HPA axis. Again, there's going to be fuzzy borders with everything. All of these are supratentorial, and we'll take a deeper look into each one of them. Okay, so we made it to our third important subcortical supratentorial structure of the brain, the basal ganglia. What we see right here is the caudate nucleus and the putamen put together, which is collectively known as the striatum, which is going to be a really important central player in the basal ganglia pathway. So here we're just looking at a sagittal slice. I'd be kind of familiar with it. It kind of looks like a headset or, a Mewtwo tail. And I would also know the coronal slice here. So here again, we have the putamen with the globus pallidus, both the externus one on the external side and the superficial side, and then the deeper internal one. The caudate nucleus is up here. The thalamus is kind of in the center of everything. And then we have the substantia nigra. So I just think of like sub being below. And then the substantia nigra really actually just means black substance, which is why this is kind of dark. And that's because tyrosine, derivatives of tyrosine are neuromelanin and dopamine are part of the same sort of pathway. So you have a lot of dopamine here, and you also have a lot of neuromelanin. Now, in between the thalamus and I guess the lentiform nucleus, which is these two together, we have this internal capsule where we're going to have a lot of axons moving, from the brainstem and the spinal cord up into the cortex, trying to get to the gray matter cell bodies up here. Here's a better picture of the internal capsule. And in my opinion, the lentiform nucleus kind of sort of looks like a candy corn. So that is just to illustrate what a horrible artist I am. That's something I drew. All right, so let's go ahead and watch this dumb video. All right, so here's the thalamus, caudate nucleus, putamen. Okay, here's GPE, GPI, substantia nigra, that's dark, and then the subthalamic nucleus. And here's everything just kind of labeled again. And all right, so we've said before, the caudate nucleus and the putamen together is the striatum. This is probably the more important name to know because I guess that's a more cohesive from a functional perspective than at least as far as my dumb brain understands, than the globus pallidus, externus, internus, and the putamen makes the lentiform nucleus, right? Like this looks more cohesive, but I think actually from a physiological perspective, we'll refer to the striatum more than we will the lentiform nucleus. All right, watch this. Watch. Boom. All right, now watch it in slow motion. Oh, that's pretty cool. That's slick. All right, so the whole idea is that when your brain is trying to it says, hey, we want to do a handshake. We want to do some sort of, greeting. That your cortex wants to do this, right? And it then is going to communicate with the basal ganglia to say, hey, like, what's the best way to make this happen smoothly? And, there's so many different ways that we can shake hands, and, it's your basal ganglia that's kind of modifying this very dumb, rough draft that your cerebral cortex does, yes to certain muscles being activated, no to other muscles being activated. And that is partly what was going to help the finished product of this, just like terrific, very precise motor movements. Boom, amazing. Can never get tired of watching that. All right, so it's really complicated. So my dumb analogy involves Game of Thrones. If you haven't seen Game of Thrones, that's fine, because if anything, some of this is going to be spitting in like Game of Thrones, like the mythology, the lore. But the cerebral cortex is the king. They want something done, and they don't really, I want to move my hand. Like, how should I do it? So the striatum is like that's the advisor they go to tell, hey, I want to move my hand. How should we get this done? The striatum is wise, and it's this is the striatum. The striatum is wise, and it's going to try to help the king. As dumb as the king is, it wants to get this done, and it's going to help try to coordinate, turning on and off different systems to get this done in the best way possible. Now, the last end of the road is the thalamus. The thalamus is the king's yes man. His goal is to always say yes to the king no matter what, because he's been around for so long, the king's always going to listen to him. So sometimes we're going to have to shut down the thalamus because the striatum says, well, the thalamus is an idiot, and we don't want to say yes to the king's request. The GP, globus pallidus, internus, and externus, I think I for inhibit. So the GPI and the GPE, they are immediately inhibiting the thing that they're always connecting to. So immediately one step downstream, always an inhibition. And I just think of them as dumb warriors, and all they know how to do is like break stuff and inhibit things. But ultimately, these are actually very different players. The GPI ultimately wants to inhibit movement, so it will inhibit the thalamus, which is trying to say yes, let's do this movement, king, sure, whatever you want. And then the E is actually trying to agree with the thalamus, and it ultimately wants to E for excite movement. Also, whenever we're inhibiting something, we're using GABAergic neurons. And then the subthalamic nucleus, I think somebody who's been under, subthalamic, that's because from an anatomical standpoint, it is right under the thalamus. But I think of it as like it's under the oppressive rule of the thalamus, and it's had enough. It wants to rebel. It wants to shut down the thalamus. All right. So the king says, I want to pick my nose. Which finger should I use? And it's going to consult the striatum, and the striatum wants to is as much of a jerk as the king is. It wants to help the king, so it's going to initiate a bunch of different things, turning on and off things to help this happen. Now, again, the thalamus is just a yes man. And it ultimately is like the last in line to talk to the king. And so it's always going to say, yes, that's a great idea, my lord. We should use the pinky finger or the index finger or whatever you said. I agree with it, right? And so the striatum's like, the striatum's actually the smart one saying, I don't know if that's a good idea. So it might have to, if it, let's say it's 50-50, sometimes the king is right, we should do this, and the thalamus is activating, we want that. So then the striatum wants to say, okay, yeah, that's sure, I'll let the thalamus activate it because that's the right course. And other times the thalamus, it's a dumb idea, and the thalamus is saying yes, but the striatum says, no, that's actually a pretty stupid thing, we shouldn't do that. So it'll then want to turn off the thalamus. So it's inhibiting these brutes, it's saying, hey, all you guys know how to do is just break stuff, like stop it. So the striatum is just not, it's not for big brutes and violence. So it's always trying to inhibit the GPE or the GPI, no matter what. That is it immediately what it is contacting with. The GPI's end goal is to inhibit. So well, that's easy. The thalamus is trying to activate always and forever. So the GPI is just going to achieve its goal by inhibiting the thalamus. Now, the GPE's goal is ultimately to excite. So a way to do that is to interact with something we don't know, turning that off, which is turning on the GPI, right? So, and if we just think about like double negatives, here's one negative and two negatives. That is going to be an activation pathway. And here I have 1, 2, and 3. 1, 2, 3. 1, 2, 3 wrongs kind of like is going to make a wrong. It's going to turn it off. So 3 negatives makes a negative, 2 negatives makes a positive. I promise this will make more in a hot second. All right, so the subthalamic nucleus is just like, I'm tired of your shit. I'm tired of being under your oppressive rule. I want to turn you off. But this person right here is a coward. They can't do it directly, so they need to go through somebody else to turn off the thalamus. So they're going to, kind of get this mercenary, this swordsmith, to this big brute. They're going to pay them to shut down the thalamus. And that also makes sense, again, because the GPI's job is to inhibit movement, and the thalamus is trying to activate movement. Okay, so the direct pathway, the king, we want to scratch a nose, and one of the king's ideas is, hey, should I like flex my index finger to scratch my nose? And yeah, if you want to scratch your nose, like flexing your index finger is probably like a useful thing. So the king tells the striatum, I want to flex my nose. And so the striatum says, let's do the direct pathway. It is going to inhibit the brute, the GPI, which is inhibiting the thalamus. Because remember, this is always trying to, the GPI is trying to inhibit movement, but if the striatum inhibits it, boom, you get movement. I would just think of like 2 wrongs make a right. Again, green is glutamate, activate. Red is GABA, which is inhibit. And so, boom. So do we want to flex our nose if we're going to scratch our nose? Yes, that is actually a smart course of action. All right, what if we, the king says, hey, should I flex my pinky finger? I don't know, you could, like, to each his own, but I don't think you're typically going to use your pinky finger if you're scratching your nose. So the striatum is like, that's a terrible idea. Like, that's not at all what we want to do. So it's going to set in motion this cascade to ultimately inhibit the thalamus, which is, again, just a yes man, always not even thinking. The thalamus doesn't think, it just says, yes, king, whatever you want, and the king will listen to it. But we want to shut down the thalamus because the striatum, the wise one, knows that's actually not a good idea. So it is going to inhibit this person who's, again, what are they trying to do? Their end goal, whether or not they're doing it, their end goal is to excite. Now, they're not doing it because they're being inhibited by the striatum. They are brute. All they know how to do is inhibit. So they inhibit the subthalamic nucleus. You remember, the subthalamic nucleus hates the thalamus because it's under the oppressive rule of the thalamus, but it's a coward, so it doesn't do it directly. So it goes to the GPI, whose end goal is to inhibit. And we have 1, 2, 3 negatives, that makes a negative. 3 wrongs make a wrong. We're going to inhibit the thalamus. We do not want to flex our pinky. So again, pinky is not flexed. And again, the direct pathway says we will flex our pointer finger. Also, just note that the indirect pathway is a bit longer. So okay, now that's and that's the simple version, believe it or not. It gets more complicated now with this substantia nigra. Now, technically, what we've had, I put it in small here. This is the substantia nigra reticulata. There's actually 2 parts to the substantia nigra. And it's really not that important. It's always just doing the same thing as the GPI. So whenever we say GPI, technically the SNR is also doing that as well. But okay, so now we're looking at the substantia nigra. And again, we have the reticulata, RET, for retarding. It's retarding movement. It's trying to inhibit movement with GABA. And then we have the compacta. And I think of compact disc, like a compact disc, a CD, and the D for dopamine. And the tyrosine derivatives are dopamine and neuromelanin. So the substantia nigra, at least the compacta version, because this is the reticulata and this is the compacta. The compacta is going to be the dark part. And so the substantia nigra, I think, is this kind of two-faced individual. One of the faces is the reticulata, and the other face, and the reticulata is typically trying to retard movement, and the compacta is going to be trying to activate movement technically. So it's kind of doing different things, but they're also working in very different ways. So the substantia nigra compacta is what we're talking about now. Again, this is just not that important. It's just doing the same thing as the GPI. So the end goal is always going to be activation for the SNC. So it sends dopamine, and they bind to dopamine 1 receptors, which are green for activating. And so all green is glutamate except for the SNC, which is going to be dopamine. So it's activating this whole direct pathway. So it's just amplifying. It's just amplifying the direct pathway. It is achieving movement that way. And it's the two-faced one. Again, it's always, the end goal is activation. So what if we're trying to do the indirect pathway, which is to inhibit movement? We're still sending dopamine, but now they bind to D2 receptors, and D2 receptors are for inhibition. So now we're inhibiting the striatum when the striatum is trying to do the indirect inhibiting pathway. And if we inhibit that which inhibits, we're going to go crazy here with all of these double, triple, quadruple negatives. We are now going to, we have 1, 2, 3, and 4. 4 negatives makes a positive, means we're going to have activation. It is trying to stop the indirect pathway and is trying to activate the direct pathway. All right, so without all my dumb metaphor, this is just what we should know. The cortex wants to get something done. It asks the striatum, which is the caudate, and the putamen. And the putamen has 2 options. It can go the direct pathway over here, and it is going to inhibit the GPI and the SNR, which is inhibiting the thalamus. The thalamus is a yes man. It's always trying to activate the cortex. Alternatively, we could have the caudate, or the striatum, go to the GPE, which is inhibiting the subthalamic nucleus, which is trying to activate the GPI and the SNR, which is again trying to inhibit the thalamus, which is trying to activate the cortex. So again, it's really just whether we have 2 negatives or 3 negatives. 2 negatives means we activate, 3 negatives means we inhibit, in direct versus indirect. Now the substantia nigra compacta, not to be confused with the reticulata for retarding movement, is trying to always activate. So the D1 receptors will activate the direct pathway, and the D2 receptors will inhibit the indirect pathway. All right, so in genetics and in undergrad, if you knock out a gene, you get to see what the effects of that gene are, right? And it's the same thing here with the brain. If we take out a part of the brain, like Phineas gauge, we get a better idea about what that part of the brain does. So we can ask, what happens if the cortex dies? You probably can't initiate movement. What happens if the advisors dies? Well, it just depends on which advisors we're talking about. So 3 common ones: hemibalism. So if you go ballistic, it's kind of like you're moving a lot, and we get this hyperkinetic movement disorder, which you can see here. And so remember that the subthalamic nucleus is part of the indirect inhibiting pathway. And so if you're taking out part of the inhibiting pathway, you're going to get more movement, which is exactly what we see right here. Now, Huntington's is the striatum. Now, remember, the striatum is Peter Dinklage. He's a nice guy. He's trying to do just make the best course of action. So sometimes that's direct pathway and sometimes that's indirect pathway. But for the Huntington's, initially in the pathophysiology of the disease, it is going to be the indirect pathway first. Now later it's going to also inhibit the direct pathway. But again, initially it's the indirect pathway that's gone. And if we don't have the indirect pathway, that means we're going to have more movement. So that is why we are hyperkinetic, because we're losing the indirect pathway. At least initially. Later you're also going to lose the direct pathway. And remember that the striatum, Peter Dinklage, is always trying to say, hey, settle down, boys, you two brutes. And so it's inhibiting the GPE and the GPI, whether direct or indirect, is always inhibiting. So if we don't have this working, we're going to have less GABA. And if we have less GABA, and that means that the substantia nigra compacta is not really being listened to, there's not going to be negative feedback that we need. So we're then going to get more dopamine, because again, the SNC is trying to tell the striatum what to do, and if the striatum's not there, it's just going to be classic negative feedback, the absence of negative feedback. So less GABA, more dopamine. If you think about it, it should settle. It should make sense. Parkinson's, we are specifically losing the substantia nigra compacta. right? The thing with the dopamine. And so if that's the case, remember, this is always trying to activate, right? It's activating the D1 with the direct pathway. It's inhibiting with D2, the indirect pathway. And so we're going to get hypokinetic or akinetic movement. So here we can see Parkinson's, not a lot of movement. Huntington's, we're seeing extra movement. And you should have less dopamine because you don't have an SNC in Parkinson's patients. All right, so nigrostriatal, think about the name. Substantia nigra, that's the dark part. The black substance. The striatum, which is the caudate and the putamen. So this is going to be coordinated movements in the basal ganglia. Mesolimbic. Mesolimbic is going to be the VTA to the nucleus accumbens, and this is really just the reward pathway, the reward processing. So you get a positive symptom in something like schizophrenia if you have too much activity of the mesolimbic system. You're going to have delusions. The mesocortical pathway is the ventral tegmented area, VTA, to the cortex, and this plays a role in regulating emotional responses to something. So if you don't have enough of this, then you're going to have a flat affect, where someone says, we have terrible news, your father has died, and you say, oh, okay. Or someone says, we have terrific news, you won the lottery, and you go, oh, okay, that's a flat affect. And the tuberoinfundibular. So we have an infundibular stalk for the pituitary system. And so that kind of is a hint. This is the hypothalamus to the pituitary. And this is going to be, it's weird. Dopamine plays a role in inhibiting prolactin. And so it's which plays a role in lactation. Our fourth significant subcortical supratentorial structure, the limbic system. For the most part, this is deep to the basal ganglia, but actually, parts are inferior and superior, and it's kind of spread out a little bit more. Kind of remind me of Cerebra from X-Men. The hippocampus and fornix kind of looks like a seahorse, and we can see this here, but let's go ahead and look at my dumb little animation. So we're highlighting on the fornix right now, and then we're going to go to the hippocampus. So now we're in the hippocampus connected to the amygdala, and then a little bit more medially, we have the mammillary body. And then the cingulate gyrus arguably is part of it as well. So we can see this again, the mammillary body is peeking up right above the pons right there. Here we have the amygdala connected to the hippocampus. It's good for the 5 Fs, fucking, fearing, fleeing, fighting, feeling, and forgetting, so arguably 6. And the fornix is a relay station, which may or may not mean that we just don't really know what it does, or maybe I just don't know what it does, but relay station. Let's just keep it simple. Hippocampus, really important for taking short-term memories and converting them to long-term memories, especially like spatial memories. So if you think of like a mouse trying to get through a maze, and it's been at it for like weeks and weeks and weeks, and it's just getting better at memorizing like parts of the maze, or if you go to a new city and you get used to like walking around, that's spatial memory. Very sensitive damage. Hippocampus and cerebellum. You think of a hippo playing with a bell. So hippo with bell, very sensitive to ischemia and whatnot. The amygdala is to do with like fearful or threatening stimuli. The mammillary body is going to play a role in the formation and the processing of memory. So it's going to be important for anterograde and retrograde memories, forming new memories, pulling old memories. The cingulate gyrus, kind of vague, but it processes emotions, whatever. It's also important for a pain response. We have this silly Venn diagram picture here just to show that there's a lot of overlap between a lot of what these things do. And again, so there's very fuzzy borders, and it's not as tight-knit as something like the basal ganglia. But you need a lot of these working together, though, to have like a functioning memory and emotional system. Also, the olfactory bulb here. This is the only cranial nerve. We have 12 cranial nerves. 1 and 2 technically don't go to the brainstem, but this is cranial nerve 1. It's the only one that doesn't go to the thalamus. Instead, it goes kind of like right to the limbic system. And so some people argue that that's why this is going to be, smell is particularly important for memory. Oliver Sacks, he writes, I think it's like the first or second chapter. He talks about a man who has Wernicke-Korsakoff syndrome. So Wernicke is going to be like the ataxia in the eye issues, and then Korsakoff is going to be for the retrograde and anterograde amnesia, both of them. And I think of people being off their rocker because there's going to be a lot of confabulation. If your brain can't remember things, your brain actually still strives for a cohesive. So it'll just kind of make up stuff to kind of fill in the gap. So it's going to be a lot of nonsense. Alcoholics have B1 deficiency. There's inflammation of their intestines. They can't absorb B1 as well, and they probably don't have the best diet, so not enough B1. Somehow that affects the thiamine disproportionately, and so they get the the amnesia. But the guy in this book, for whatever reason, he can remember things like before 1945, and so he he thinks he's a young man in the Navy, and it's like a really sad moment where Oliver Sacks like shows him a mirror, and he freaks out because he realizes how old he is. And I think some of this was the inspiration for 51st Dates. Our fifth subcortical infertentorial structure is the thalamus. A lot of people think of this largely as a relay station. A lot of the motor inputs have to move through here and sensory inputs move through here. Keep in mind that the one sensory modality that does not move through the thalamus is the olfactory sense. So there's a lot going on in the thalamus, right? It looks just like one big old blob, but it really is broken up into several smaller components, each of which has a very specific and particular role to play. So we'll be looking at the anterior part, the ventral anterior part, the ventral posterior parts, the medial and lateral perspective, and then the geniculate nuclei. So the anterior, I just remember that this is next to, if you know your anatomy, your geography of the brain, we can see that the anterior nucleus here is next to the fornix, the hippocampus, mammillary body, and amygdala. So it should be no surprise that this plays a role in memory if you can remember and recognize that. The ventral anterior, so one dumb way you can think of this is like the VA, it's a government institution, the Department of Motor Vehicles, government institution. And so this has to do with the motor functionality of a person. You can also remember that it's next to the basal ganglia, right? This ventral anterior is right next to this, the lentiform nucleus, specifically the globus pallidus internus. It's directly adjacent. Also, if we think about like precentral, so once you're above the spinal cord and the lower medulla, we start to see motor things push towards the anterior and sensory things push towards the posterior, right? Just think of the precentral gyrus in the anterior side of the frontal lobe and the postcentral gyrus posterior in the parietal lobe. And it might help you remember that because this is in the anterior portion, this has to do with movement. And then quite the reverse here with the sensory part. This is in the posterior aspect is the ventral posterior. And so this is postcentral gyrus associated. And so it's going to be sensory modalities. Medial has to do with the face. Some people think of M for makeup and then like L lateral for limbs. And then sometimes if you have like an infarction of the PCA that fuels the posterior aspect of the thalamus, you might get thalamic syndrome where you have associated pain after the stroke has subsided. Then we have the lateral geniculate nucleus and the medial geniculate nucleus. I think of L for light. You can also, and this is going to ultimately transmit things from the optic nerve to the superior colliculi. I think of S for sight. You can also remember of the superior colliculi is above the inferior colliculi, and the eyes are above the ears. So superior colliculi is for the eyes, and then the inferior one is for below for the ears. And this is going to come from the auditory cortex via the medial geniculate nucleus to the inferior colliculi. So you can think of M for music. So here I have a picture just of the vision pathway, which is probably the more important one. So we're going to be starting with the optic nerve, the optic tract. So this is the optic chiasm, and then let's just follow this. And go. All right, to the lateral geniculate nucleus from the optic tract, into the superior colliculi, just to contrast this now, showing the inferior colliculi. Okay, our sixth and final subcortical supratentorial structure is the hypothalamus and the pituitary system, which together work in an axis. So we have our anterior pituitary and our posterior pituitary, and they're going to be communicating with the hypothalamus. Recall that the anterior pituitary makes its own hormones. The posterior pituitary is sort of gifted these hormones, oxytocin and ADH, from the hypothalamus. The hypothalamus communicates with the anterior pituitary via its own hormones: growth hormone releasing hormone, gonadotropin releasing hormone, prolactin releasing hormone, cortisol releasing hormone, and then thyroid releasing hormone to stimulate our flat peg hormones, FSH, LH, ACTH, TSH, prolactin, endorphins, and then growth hormone. Endorphins we can ignore. And then these are going to have all sorts of interesting downstream effects. And we're going to talk more about this in the endocrine system, so I wouldn't go too crazy with recalling all of this, but you guys should be roughly familiar with this via the MCAT. So the anterior pituitary is again connected via a portal system with the hypothalamus, while the posterior version has neurons, which basically deposit the hormones via vesicles across synapses. The anterior pituitary is derived from Rathke's pouch, which is ectoderm derived from like oral tissue, while this is derived from neural tissue, ectoderm, specifically the diencephalon. So there's different embryological origins between the anterior pituitary and the posterior pituitary. And that seems kind of random, but in esoteric, and it is, but it's something that comes up occasionally, so I would know it. Connecting these two is what's called the infundibular stalk, which is much more elongated and thin than demonstrated in this picture. So actually, we're going to see like a kind of an overview here. So starting with the thalamus, let's take a look. Okay, under the thalamus, of course, under the thalamus, hypothalamus. The ventricle, the third one, is right in between the thalamus on the left and the right. Okay, here we have the long infundibular stalk that I mentioned, right under the optic chiasm. Let's get that away, and then right there we have our little pituitary gland, which is sitting in the sella turcica of the sphenoid bone, Turkish saddle. I don't really know what a Turkish saddle looks like, but apparently it looks like that. So this is our, we're really just putting emphasis here on the hypothalamus. And this is pretty much the same picture. Hypothalamus is kind of this like master sensor, right? It has spies everywhere. It's picking up salt and pressure and acidity and temperature to try and regulate a homeostasis for the body. So paraventricular nucleus, I think of like O and P being next to each other. So this is the one that makes oxytocin. Anterior nucleus is for cooling. I think of AC, anterior cooling. There's going to be a lot of like contrast, opposites. So and the antithesis of this is then the posterior nucleus, which is going to deal, if the anterior is for cooling, this one is for heating. You can also think of like hot pot. Preoptic nucleus. So pre-op is it's a term used to describe transgender, transsexual, or gender non-conforming people who have not completed gender reassignment surgery, but who desire to and are seeking that as an option. And if somebody is planning on getting surgery, they might be taking some sort of gonadotropin releasing hormone therapy, exogenous therapy, to supplement their transition. So I just remember the term pre-op goes with GnRH. So however you can make it stick. Supraoptic. So I think of like supra, something being too high. Well, if your sodium's too high, then your body might go ahead and say, oh crap, we should release some ADH to raise the blood pressure and some vasopressin to dilute it to bring the levels down. So supra is sodium's too high, ADH would be released. The suprachiasmatic nucleus. So this, in response to light, is going to inhibit the pineal gland from secreting melatonin. The not depicted here, but the ventrolateral nucleus. I think like lateral is like you're reaching out with your extremities for food. So reaching out for food, that's going to be hunger. And the opposite of that then is medial, which is satiety. So things like leptin and ghrelin are going to be working here. As we mentioned, light is going to stimulate the SCN, suprachiasmatic nucleus, which is going to inhibit the pineal gland from secreting melatonin, which helps us sleep. Here is a picture of or depiction of the pineal gland here on the posterior side of the hypothalamus-thalamus structure. So as far as sleep goes, I would remember bats kind of drink blood. So when we're awake, we have beta waves. We're a little tired, we're meditating, we get alpha waves. Just started to fall asleep, you get theta waves. Stage 2, you're going to get the, bats, you get sleep spindles and K complexes here and here. Then delta wave, I think of D for deep. This is going to be your deep sleep, so stage 3 and stage 4. And sometimes this is referred to as slow wave sleep. And then REM is for rapid eye movements, because kind of interesting because your muscles are mostly paralyzed, but your eyes are fluttering quite severely. You can look this up on Google. It's kind of interesting. Or just observe your partner or buddy when they're sleeping weirdly. So this is paradoxical. And for whatever reason, I forget why I started this lecture a long time ago. They study ostriches. I guess they have like severe and easily observed changes in slow wave sleep versus REM sleep. But I just thought that was kind of random and hilarious. In REM sleep, as you can see, the pattern actually looks quite similar to being awake. Again, why it's paradoxical. let's say I'm trying to unicycle and I want to learn how to like unicycle. I want to make sure I get some REM sleep because that's going to help cement this understanding, this memory in my head. Let's say I get my first kiss today, or I have my wedding today, and I really want to remember this day. Well, emotional memory consolidation is going to be important too. During REM sleep, we said you lose motor tone. This is where dreaming occurs. This is where men might get erections, and elderly people are going to have less REM sleep. Looking at the deep sleep, slow wave sleep, delta waves. So if you want to remember something before your test, this is the declarative memory, the facts that your Anki cards is going to be consolidated here. So that's going to be particularly important. And some people just consolidate this to stage 3 and don't differentiate it. Bedwetting will occur here. Now, this is the deepest sleep, hardest to arouse somebody, and also down in the elderly. And see that this kind of we're here. Maybe like hour and a half, we're going to get these little REM cycles. And you skip past, so this y-axis here is kind of showing how deep the sleep is. So you actually skip past REM sleep here the first time, but then we just kind of go through these nice cycles. As we go down, 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 up, 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 REM. Sometimes you awake briefly, just for whatever reason, you're not even aware of it, you don't remember, or maybe you got to go pee. But again, like every hour and a half. So if you want to set your alarm 7.5 hours or 9 hours apart, would be ideal so that you hit just the end of a sleep cycle. So brain's crazy important, right? It's like 2% of our body mass. It's 25% of our energy demands. There's not a lot of glycogen in the brain, so it's really prone to ischemia and needs a lot of food. It's also vulnerable for a bunch of reasons, though. It's really, really soft tissue. So it's really, really important that the body takes steps to protect it. It does this with the blood-brain barrier, which, some things like glucose and amino acids will be typically allowed in, although they're regulated, but a lot of other things are outright banned as opposed to normal systemic circulation. And this tight blood-brain barrier is achieved through tight junctions of astrocyte foot processes in a thickened and tougher basement membrane, just to keep it from harm. But so this isolation is a double-edged sword, right? So if you're extra protected from bad things in the body, well, that also means you might be protected from information that we might have in our blood. It also means it might be difficult to get information out into the blood if we need to. So there's a trade-off here. So to circumvent this, we have a couple of circumventricular organs. So normally, again, we can't get through because we get these tight junctions and these foot processes, etc. But we have these sometimes fenestrated capillaries where things are allowed through circumventricular because they are near certain ventricles in the body. And this allows, chemicals, whether good or bad, maybe to have a little bit of access to brain tissue. So some of these we've already talked about. So the pituitary gland we've talked about, and this makes sense. We got to secrete hormones to the blood. Pineal gland, we need to put melatonin into the blood to help us sleep. A couple that we haven't talked about, though. So in the hypothalamus, the OVLT has osmoreceptors for sodium. And again, we said like if sodium's too high, supra is going to release ADH. But then we also have the SFO. So this is in the third ventricle. This is in the interventricular foramen, also known as the foramen of Monroe. This is going to have baroreceptors, also going to be for ADH release from the supraoptic nucleus. The median eminence, we said that the hypothalamus needs to communicate with the pituitary, and this is how it does, gonadotropin releasing hormone from the preoptic, the TRH, CRF, etc. Then in the medulla, we have the area postrema. This is going to detect toxic chemicals in the blood, and it's going to help regulate and inform the vomiting center. So the area postrema, I would just think it is the chemoreceptor trigger zone, the CTZ. Some people say the AP is in the CTZ. Some people say the CTZ is in the AP. I don't think it really matters. I think the AP is more of a geographical term. That was first. That was the first coin. They just knew the geography yet, and then later they figured out what it was, and they said it was the CTZ. But the Venn diagram between AP and CTZ, in my opinion, is like a circle. So I would just think of them as pretty much the same thing. And then the choroid plexus, technically, you could think of it as a seventh one, but it doesn't really count. It has permeable capillaries, which can allow, aspects of the brain to interact more directly with the bloodstream. But it doesn't actually have like neural tissue and neurons. So arguably, it doesn't count. Okay, as we continue our descent from the top of the cortex down to the bottom of the spinal cord, we're finally passing this tentorium cerebelli layer. So we're descending from the supratentorial structures down into the infratentorial structures. In first stop, really to talk about is the brainstem. Except it's not, right? We really can't get into the brainstem until we talk about the cranial nerves, because so much of the brainstem really has to do with the cranial nerves. I would say that's the most important thing about the brainstem. As we look, this is an inferior to superior view of the brain. The numbering is kind of reasonable, right? So this is on the anterior side, and then we're moving kind of from the anterior to the posterior and the superior down to the inferior a little bit, right? But like 1, 2, 3, etc., all the way down to 11 and 12. A better way to organize them, though, is the rule of fours. So the rule of fours says there's going to be 4 cranial nerves in the medulla, 4 in the pons, and 4 above the pons, right? So that we're very specific with the language there, because that means there's actually 2 in the midbrain, and then there's also going to be 2 in, not really in the thalamus, but coming off of the thalamus and in the limbic system and whatnot. So the olfactory bulb goes to the limbic system. The optic nerve goes right into the thalamus and the lateral geniculate nucleus. Then we have 3 and 4 in the midbrain, 5, 6, 7, 8 in the pons. Now, there's going to be a little bit of overlap. Trigeminal nerve is really big. It's going to kind of go all over. Cranial nerve 8 is right on the cusp, a little bit in the pons, a little bit in the medulla. That's going to be important for strokes later when we're looking at the pica and the aorta strokes. And then we have 9, 10, 11, and 12. On top of this, anything divisible by 12 is going to be midline. So that's like, 3, 4, 6, 12, and anything not is going to be on the lateral side. So we'll more in the rule of fours later, but this is definitely this is a must now. All right, starting with the olfactory bulb. So it projects from olfactory foramina on the cribriform plate, which is itself part of the ethmoid bone. And it's the one sensory nerve that doesn't go straight to the thalamus, right? It doesn't go through the thalamus. It goes through the limbic lobe. And people argue that this is why it might be important for, you walk into a house, you smell something, you go, it reminds me of my grandma or something, right? That's why, arguably. Here's a fun picture. And here's a fun picture as well, going through these the foramina of this cribriform plate on the ethmoid bone. Optic nerve. So this is all afferent incoming information. So we have the optic nerve, which goes to the optic chiasm. Some of it goes ipsilaterally, some of it goes contralaterally. And note that the pituitary bulb is right there. So again, it goes optic nerve to chiasm. After this, though, so it splits. Some of it stays ipsa, some of it goes contra. Now it's the optic tract, which goes through the lateral geniculate nucleus, and sometimes some of the reflexes go to the superior colliculi. Sometimes we don't, and don't worry so much about when we do and when we don't. We then go through either the dorsal, sometimes known as Baum's, we'll talk about that, or the Meyer occipital radiation. So we go from a tract to a radiation, and then we go to the occipital lobe for, or that's our destination for visual processing. So let's go ahead and just take a look as we move through this. Optic nerve, optic chiasm, optic tract, lateral genicular nucleus, superior colliculi, occipital lobe. Not shown are the dorsal and Meyer occipital radiations, because I think they're just too thin. All right, so there's going to be a lot of crisscrosses, right? I think I labeled like till 4 or 5, and then it's overkill. In all of neuro, there's just so much crisscrossing, so much decussation that you really just got to keep track of it. They love to ask these questions because they're hard. So everything in the left visual field is going to go to the basically right part of the brain. Everything in the right visual field is going to go to the left part of the brain. But it's a little bit more complicated, because if you imagine the left visual field here, some of it is going to go to the nasal retinal fibers. These are the ones that are going to go through the optic chiasm and cross. Now the part over here that's getting the temporal retinal fibers is getting the right visual field. That's actually going to stay ipsilateral and move down. So these tracks are going to be some of the ipsilateral side and some from the contralateral side. If you imagine this is like an intersection, though, it should make sense that the nasal fibers would be the one to cross, because they don't have to cut across as much traffic as it would be if it was a temporal fiber that's crossing. We said that after the lateral genicular nucleus, we get these optic radiations, which are going to go to the parietal lobe, and these Meyers, which are going to go to the temporal lobe. And some people call this Baum's loop, but there's kind of an interesting article about how no one actually knows where the term Baum's loop came in. Some article publication just mentioned Baum's loop, and everybody copied that article, and people copied the articles that copy that, and somehow it spread like wildfire. It's this kind of weird meme, and it doesn't actually mean anything. No one actually, is kind of made up. So I wonder if I put in one of my lectures like the Cartonis lobe and somehow it proliferates and it becomes a thing. But it's kind of like the Caesar salad, right? Caesar didn't eat salad, somehow that became named after him. But again, Meyer is going to go temporal and optics is going to go more parietal. And that's going to be important when we're looking at lesions. So the left part of the brain is the right visual field, and so everything's opposite. Same thing here. When we go to the upper dorsal optic radiation, it's going to actually be the lower part of the visual field, and the lower Meyer tracts are going to be the upper visual field. So let's talk a little bit more about the optic chiasm. So the optic chiasm, as we said, is sitting right next to the pituitary gland, which is sitting in the sella turcica right here. Oculomotor. So the oculomotor is really just, it's in the name, oculo, eyes, motor, muscles. So this is, it's coming from the midbrain, right? So remember 1 and 2 are technically not from the brain stem, but 3 through 12 are, with kind of the exception of 11. So this is all of the muscles of the eyes coming from the midbrain. Again, we remember 2-2-4-4 rule of force. So here's all of the different eye movements we can deal with, and most of them actually are going to be the oculomotor. So when in doubt, it's the oculomotor that's doing things. We're going to go through all of these. So superior rectus is going to pull it up. The inferior oblique pulls it kind of up and medially. The inferior oblique pulls it up immediately. Inferior rectus just pulls it down, and the medial rectus pulls it medially. Ptosis, so the oculomotor, also the levator palpebrae superioris, is going to really just keep this eyelid pulled back. So that's a functioning oculomotor, and this is not a functioning. So you're going to have this ptosis, the drooping eyelid, if you have a problem with your oculomotor nerve. Notice that you can also get this if you have Horner syndrome and an issue with sympathetic innervation of the face. And that's because originating off of the levator palpebrae superioris is the superior tarsal plate, which is supplied by the sympathetic nervous system. So you can actually get a similar phenotype here. So the oculomotor nerve in our midbrain is right next to the Edinger-Westphal nucleus, which has a bunch of parasympathetic fibers which are going to innervate the pupil for constriction. And so these travel kind of in a bundle here. The oculomotor is going to be on the inside, the deep part, and the parasympathetic nerves are going to be in the periphery. The oculomotor is going to go ahead and supply all of these muscles. And that one, and the parasympathetic is going to help constrict the pupils in response to light. So we have a nice picture here. So imagine if you had ischemia, right? You're severe diabetic, or hypoperfusion, or hypertension, or for whatever reason you can't get adequate blood flow. The parasympathetic nervous system, right, to the pupils to constrict is actually going to be fine, because the blood's coming from outside and going in, and so this is going to be less likely to become ischemic. This is more likely to become ischemic. So you should have an issue with your eye muscle movements, but the pupillary dilation constriction should be fine. On the other hand, if I have a tumor, the tumor potentially could be the opposite. It could just hit the pupil, and then you have a pupil issue. But actually more likely that if you have a big tumor, it's going to hit both. But so that's a really important thing, is that a tumor is going to hit both, or just the parasympathetic, while ischemia is going to hit both, or just the oculomotor on the inside, because it's deeper, it's more distal from the blood supply. So if we, there's a lot going on here. So we see cranial nerve 3 popping out over there. This is very susceptible to saccular aneurysms next to the posterior communicating artery. So here we're looking kind of at the circle Willis, which we'll talk about later, but you get a lot of saccular aneurysms here, also known as berry aneurysms, because they kind of look like a berry. Sometimes they're called saccular aneurysms because they kind of look like a sac. And if these rupture, if there's a hemorrhage here, you're going to get a subarachnoid hemorrhage. And often again in the PCOM, this is going to go ahead and damage the cranial nerve 3. And so boom, and that would damage cranial nerve 3. Again, technically, it's going to hit the parasympathetic first, but likely it's going to hit both of them. You could also damage the oculomotor nerve if you have an uncal herniation. So if you have some sort of hematoma and there's a mass effect and there's a lot of pressure pushing this way, you could have a tentorial herniation, and we know that right at the bottom of the tentorium is this 3rd cranial nerve, which could get damaged. We mentioned the Edinger-Westphal parasympathetic innervation on the periphery. This is going to be for pupillary constriction. These are the sphincter muscles. You also have dilator radial muscles, which are going to be sympathetic. So there's a pupillary reflex if light comes into your eye. So if light comes in, it's going to move through your eye via your afferent optic nerve 2. It's going to go to the pretectal area in the posterior of the midbrain. It then moves to both Edinger, the ipsilateral and contralateral Edinger-Westphal nucleus, which is going ahead and send efferent fibers outwards via these parasympathetic ganglia, which are going to run alongside the oculomotor nerve, and they are going to activate the constrictor, sphincter muscles to close the pupil. Because if you're shining a light in your eye, you don't need that much light. So constricting is the smart move. Here's just a cool little thing. We go to the pretectal nucleus, then it goes in the Edinger-Westphal, and then it goes back out, and it's going to cause constriction. So there's the light reflex, but you have a similar constriction reflex. So here's your light reflex, right? That's constricted. This one's not. But if you bring like a pen close to your face, anything close to your face, your pupils are also going to constrict there. And the idea is you want to minimize these widely, as you bring something really close to your face, you're getting widely diverging rays. And those are going to hit the sides of your retina. It's going to confuse your brain. So by constricting, you're going to allow less diverging light to come in. Similarly, your eyes, your medial rectus muscles are going to kick into gear, and by moving inwards, we're also going to direct the light to the back of the retina rather than the periphery of the retina. So you're going to have less diverging rays. And on top, so that's number 2. And number 3 is you're going to activate your ciliary muscles, contract it. And when you contract them, so here's our lens. If this is something far away, we're not contracting. We have a very thin lens, and so it doesn't really converge much. But because something is far away, these lines are mostly parallel, so we don't really need to converge them that much. But if something's really close, again, we have diverging rays, and we try to literally accommodate for this by constricting the pupils, medial rectus kicking in. But we're also going to want a super fat lens so that we can hyper converge these diverging rays. So that again, we still have everything hit right at the retina, which is what we want. Trochlear nerve, this is coming from the midbrain, but it's actually coming from the back of the midbrain. It's like, I think the only cranial nerve that I can think of that really comes from the posterior aspect. So it's going to loop around a little bit. It controls, so I think of SO4 because it controls the superior oblique. Inferior oblique, most of these muscles make sense except the superior and inferior oblique. So really just to hit home, the superior oblique, it's the superior oblique muscle, but it does the opposite of what it says. It's going to bring it inferiorly. Now it also brings it medially. So just commit this to memory. Superior oblique is going to bring your eye down and in. That's cranial nerve 4. Inferior oblique is the oculomotor. This is going to bring your muscle in your eye in and up. And so this trochlear nerve is going to be useful if you're reading a book or you're walking down the stairs, because you kind of have to bring your eyes inwards and down to do both of those things. The trigeminal nerve, so this is coming from the pons now, the rule of 4s, right? We had 1 and 1, 1 and 2 is above. Just 2 and 3 is going to be the midbrain now. 4, 5, 6, 7, arguably 8 are going to be now in the pons. So mostly sensory, and it's really 3 nerves for the price of 1, since the name tri. And V1 is just going to be the ophthalmic to the forehead and the eyes. 2 is going to be maxillary to the kind of the teeth and lower part of the nose. And then the mandibular is going to be to the muscles of mastication in your jaw and whatnot. So here we have the ophthalmic distribution. Here we have the maxillary distribution. And here we have the mandibular distribution. Again, we said mostly sensory, but there is some mastication, some efferent motor neurons involved in the trigeminal nerve as well. It's also going to innervate the anterior 2/3 of your tongue. So specifically, it's going to be your, this says lingual nerve, sensory. Maybe ignore what this says. No, I'm sorry. Don't ignore it. Sensory in the sense that, like, if you're eating something really hot, that's what your trigeminal nerve is going to pick up on, your mandibular V3 nerve. So not does it taste good, not does it taste bad. It's just, is it hot or cold, or is there something there? So yeah, sensory in that sense of the word. Abducens, abduct. It's going to abduct your eyes. This is also coming from the pons, and boom, this is going to pull your eye out into the side. It's abducting. The facial nerve, it's going to kind of be the opposite of the cranial nerve 5 in a couple of ways. It's the motor, efferent to most of your face. It's also going to supply a lot of the glands, except for your parotid, which is kind of ironic because it actually moves through the parotid, and for whatever reason it doesn't innervate that. Also plays a role as the stapedius muscle is innervated by this. The stapedius muscle is going to help with your the stapes and the ossicle bones in your middle ear, and it's going to help regulate sound. Also now not so I kind of sense was the V3, but this is now taste. Oh, this is too sweet. This is too bitter. That is going to be the facial nerve. So here we're just seeing a dumb picture. There you go. Proof. It goes right through the parotid gland. More proof. It goes through the parotid gland, but it does not innervate the parotid gland. It innervates most of the other glands, though. And we're kind of see this here specifically as the chordae. The tympani is going to be a downstream derivative, basically a branch of the facial nerve, and it's what's going to supply the taste to the anterior 2/3 of the tongue and certain glands that are going to help with salivation. So again, anterior 2/3 of the tongue's sensory was the cranial nerve 5, but now this is taste. It's cranial nerve 7. So we said it's most of the muscles of the face. It's probably the most important thing about it. Is something like Bell's palsy. And we'll talk about this later, but if you get a Bell's palsy, cranial nerve 7, it's going to be the entire face. If you have an upper cortical stroke, it's actually only going to be the lower part of your face. It's going to spare the forehead. But you're not going to be able to move the temporalis muscle, so you're going to, it's kind of like you have Botox now. So inability to wrinkle the brow. The orbicularis oculi is useful for closing your eye. And if you can't close your eye, then it's going to kind of be like the opposite of ptosis, where it's going to keep your eye extra open. Inability to puff out your cheeks and smile, so it causes a drooping of the mouth. And yeah, so if you see somebody with this, it truly is hard to miss. And we mentioned it also innervates the stapedius muscle, which helps regulate the stapes in the middle of the ear. And so if something's wrong here, you're going to have something called hyperacusis, where the sound is going to sound incredibly loud, just like a normal conversation. Vestibulocochlear nerve, this is going to be 2 for the price of 1. So vestibulobalance, cochlear, this is going to be hearing, also coming from the pons, but it's kind of the medulla too. It's a little tricky. And it's going to parallel the facial nerve in a bunch of different ways. This kind of makes sense if you think about the fact that the cranial nerve 7 goes to the stapedius. So cranial nerve 7 has something to do with hearing. So it makes sort of sense that 7 and 8, then being so close to one another, kind of have slightly parallel roles. We see evidence of them paralleling literally the geography right there. But then it's going to bifurcate. And some of it's going to go to the semicircular canals, and some of it's going to go to the cochlea. Glossopharyngeal nerve. Glosso is tongue. Pharyngeal is the pharynx. Again, 2 for the price of 1. So it's going to help with swallowing related activities in the pharynx. And also it's going to pick up on, so we have these carotid bodies in our carotid artery, which are going to have lots of baroreceptors. So if your blood pressure is too high or blood pressure is too low, it's going to send sympathetic or parasympathetic signals to your heart to regulate your stroke volume and whether you have tachycardia or bradycardia, and should we dilate the blood vessels or constrict the blood vessels. So this is going to be picking up blood pressure and helping inform a response. Now this is, again, we have a lot of nerves to the tongue. We have 5 of them. So this is the third one. This is going to the posterior. But this is doing both the sensory and the taste to the posterior aspect of the tongue. So again, the cranial nerve 5 was just the sensory as a hot or cold to the anterior 2/3. Facial was just the taste of the anterior 2/3. This is doing temperature, pain, the sensory, but also the taste to the posterior 1/3. So a gag reflex, if you poke in here, you're gonna gag. You just don't ever think what a gag reflex is. Cranial nerve 9 is going to be the afferent, sending the sensory information in, but then the motor efferent is going to come from cranial nerve 10. So these two things are going to work together for this. The vagus nerve, cranial nerve 10, this is coming from the medulla. There's a lot of roles, parasympathetic to the GI system. Soft palate elevation, midline uvula. These aren't really that important, but it's going to be really important for diagnostics. We just said it's the afferent cough reflex, and it's going to help with swallowing as well. Because it controls a lot of the muscles, again, that play a role for a gag reflex, and so similarly, it's going to play a role with swallowing as well. So we just said gag reflex, 9 and 10. Palatal reflex, though, is just going to be 10 only, touching the roof of the mouth and watching it go up. You're in a picnic, parasympathetic nervous system, you want to digest your food, your vagus nerve is going to help with this. And the recurrent laryngeal nerve is actually going to branch off this, go under the aortic arch, and is going to go up and innervate a lot of your the muscles. You're just helping with your voice box. And so if you have damage to the vagus nerve, this is going to cause hoarseness. And that's going to be really helpful for isolating a type of stroke that you might have. We also have, so cranial nerve 9 got the baroreceptors in the carotid space, but we also have baroreceptors in the aortic space, and cranial nerve 10 is going to pick up on these. So yeah, again, we have the 9, and here we have 10. Accessory nerve. So this comes from the cervical plexus, which makes it a little bit unique, right? It's not actually coming from the brainstem. It's actually coming from cervical plexus a little bit down below. Think like C2, C3, C4, C5. It innervates the sternocleidomastoid muscle for turning the head. So it's originating from these cranial nerves, and it's actually moving up, which is kind of weird. It's moving up. It moves the foramen magnum, and then it goes back down through the jugular foramen, kind of paralleling cranial nerve 8 and 10, which is interesting. So it's the SCMs for turning your head. So this would be the right SCM from the right accessory nerve, helping turn the head to the left. And then we have these trapezius muscles, which are also going to be a little bit innervated by the accessory nerve. Hypoglossal, underglossal tongue. So it's under the tongue is what this is innervating, and but it's largely actually for projecting the tongue forward. So it's going to be most of the motor output for the tongue. So yeah, motor output, a lot of the muscles here. And so we kind of ignored a little bit the vagus nerve in the tongue. I don't think that's so important. So it's the hypoglossus is going to be pushing your tongue out. Very important. And if you have a lesion here, let's say you have a lesion in the left side, you're going to have your tongue is going to bend towards the left. And people remember this by you lick your wounds as your tongue is leaning to the left, because that's the side where the damage is. So reflexes, for the most part, the numbers are always going to be lower. So the corneal reflex, if somebody pokes your eye, you're going to blink. And you're feeling this with V1, the ophthalmic, and you're closing your eye with the orbiculus oculi with cranial nerve 7. The jaw is going to actually be both the V3, the mandibular, for the sensory and the motor. The gag, we said, is 9, and then mostly 10 for the efferent. And then the pupillary, constriction response to light, 2 is going to be the afferent, and then 3 is going to be the efferent. So when in doubt, the lower number is always going to be afferent. So just a little summary. I actually think all of that's really high yield, but if you didn't get any of this, 1 is smell, 2 is afferent, the optic nerve, 3 is going to be efferent, controls most of the muscles, 4 is going to be specifically the superior oblique. Remember, SO4 is how I remember this, and it kind of does the opposite of what it says. The superior actually brings your eye down, and so it's specifically going to be down and in. So you want to read a book, you want to look down the stairs, you need your cranial nerve 4 to be working, the trochlear nerve. Cranial nerve 5, V1, V2, V3, forehead, middle of the face, lower part of the face, V3, the mandibular, is also going to be playing a role in mastication. 6 is going to be the abducens nerves, pulling your eye out laterally. This is a lot. This is all of the glands except for parotid, which it moves through. It's the stapedius or hyperacusis is going to be a thing, and it's the motor output. So you're going to have Bell's palsy, including the forehead if this is damaged. Also, the anterior 2/3 of the tongue for taste for this, and the anterior 2/3 of the tongue for is this hot or cold. Vestibulocochlear is going to be, the vestibular is going to be balanced, cochlear is going to be for hearing. This is going to be for the gag reflex afferent. It's also going to be for the carotid sinuses, baroreceptors. 10 is going to be the vagus nerve, which does a lot of different things. It sends parasympathetic innervation to the GI. It's going to be the efferent part of the gag reflex. Does a whole bunch of things, palate elevation. 11, the accessory nerve, is coming from the cervical plexus, but remember, it goes upwards through the foramen magnum and then goes down through the jugular foramen with everybody else for turning your head, also the trapezius stimulation, and then the tongue pushing out as the hypoglossus is going to be the motor. And I left something out, the cranial nerve 9 is also going to be for the, we said the lower part of the, the posterior 1/3 of the tongue for the sensory and the taste. So now we looked at the inferior to superior, and now we're looking downwards, eagle eye view. And again, we can kind of see cranial nerves, 1 and 2 all the way down to 12, moving in this particular direction. So actually, it sounds super esoteric, and it is, but you got to know this. So 1 goes through the cribriform plate, 2 goes through the optic canal, superior orbital fissure. This is going to be almost all eye-related stuff, like 3, 4, and 6 are all eyes. Cranial nerve, this V1, this is actually all eyes as well, right? This is the ophthalmic, which is the sensory to the part of the eye part of the face, the upper part of the face. Cranial nerve 2 is the foramen rotundum, and cranial nerve V3 is going to be the ovale. Middle meningeal artery, where the which if you get this ruptured, you can get an epidural hematoma, goes through the spinosum. And then we have all of the ear stuff, 7 and 8. It makes sense; those go together. Goes through the auditory meatus, the internal one, and then a bunch of things go through the jugular foramen. We said it's 9, it's 10, and 11 goes upwards through the foramen magnum and then goes down with everybody. But it's called the jugular foramen, so also the jugular vein goes through here. The hypoglossal canal, it's going to be cranial nerve 12, and that it's literally, that's its namesake. And then the foramen magnum is, well, this is where the brainstem is going through. We said the cranial nerve 9 is going to be going up, and then the vertebral arteries are coming through here to form to make the basilar artery. Okay, now that we have a better understanding of the cranial nerves, we can actually get to the brainstem. So the brainstem, we have the midbrain, we have the pons, and then we have the medulla. You should be able to kind of sort of like, notice features from anterior, posterior view. This giant thing hugging the face, this big fat protuberance is the pons. You have these long, like striated longitudinal tissue. It's going to be your medulla, and then they desiccate in the lower medulla. Looking at the posterior side, we have the quadriminal plate, quad because there's 4. There's 2 superior colliculi and 2 inferior colliculi. And then right on the posterior side of the thalamus, you have the hypothalamus, you have the pineal gland. And remember, the trochlear nerves are kind of the only ones, the cranial nerves, that really come from the posterior side. You notice that everything else really comes from the anterior side. And again, you can notice when we're looking at the medulla because we have these longitudinal sections in the vertical plane. So the rule of 4s, again, there's 2 cranial nerves above the midbrain, 2 at the midbrain, 4 at the pons, and 4 at the medulla. If you divide evenly by 12, you are in the midline. If not, you're probably going to be in the lateral. There are a couple exceptions where you have the nucleus actually in the midline, and then the actual nerve itself kind of then quickly moves over to the periphery. In general, we're going to have 4 midline structures that begin with M. The motor nucleus, the MLF, which is in the midbrain and pons for the most part, the motor pathways, and then the medial lemniscus. And then the side structures, we're going to have 4 of them that begin with S. Again, rule of 4s. Spinocerebellar for going to the cerebellum to help with coordination. Spinothalamic tracts, sensory and sympathetic. Note as well that the medial lemniscus, we call it this in the brainstem, but in the spinal cord we call it the dorsal column, so it has a name change. That name change also reflects what it does. It moves medially, which is helpful, as opposed to being very dorsal in the spinal cord. Okay, so looking at the midbrain, the cerebral crus, also known as the peduncles. These attach the cerebrum to the lower brainstem. This is going to be a lot of your motor output. And again, once you get above the spinal cord, you can just kind of keep this in mind, right? The precentral gyrus is going to have your somatomotor cortex, and then you have your somatosensory cortex a little bit on the posterior side. And it's the same thing for sensory is probably going to be more on the posterior axis, and motor is going to be more on the anterior axis. It is useful to remember. So speaking of which, the medial lemniscus and the spinothalamic tract are going to be right here. Again, we have the anterior over here is the motor, and then a little bit posterior is going to be the sensory. And as the name implies, medial lemniscus, which is proprioception, is going to be a little bit more medial than the spinothalamic tract, things like pain and temperature. We have the tectum, which is kind of this area, the tegmentum, which is kind of that area. I know it's pointing to the red nucleus, but it's like this whole area over here. The ventral tegmentum area sometimes can produce dopamine. Remember, this is in the mesolimbic and mesocortical pathways. We then have the substantia nigra compacta, which is it's always in the activating the directing, and it's inactivating the indirect pathway. And it's dark, substantia nigra, black substance, neuromelanin, and dopamine are both downstream derivatives of tyrosine. So it makes sense that you'd kind of have a little bit of both if you have a lot of tyrosine production here, tyrosine manipulation. And the tectum is going to be, back here in the back, is going to contain the colliculi. So I kind of differentiate tectum versus tegmentum with the C and C for colliculi. Cranial nerves 3 and 4 divide evenly by 12. They're going to be kind of midline. The red nucleus, this is only going to be in the upper midbrain. It's going to be for the upper limb flexors, which we'll come back to. This is important for decorticate and decerebrate posturing. And the Edinger-Westphal nucleus, which is just a cool name, objectively, is going to parasympathetic. It's going from the pretectal, so optic nerve afferent to the pretectal to the Edinger-Westphal nucleus. The parasympathetic now is going to send things along the oculomotor nerve to help constrict the pupils as far as the pupillary light reflex. And the MLF is going to be important for coordinating lateral gaze. Whew, that's a lot. Medium yield, stuff you should know. All right, the red nucleus is always trying to flex your upper arms, but it's up to your brain to say, stop doing that. This happens for a lot of primitive reflexes as well, right? The Babinski, you want to point your toes towards the ceiling, and your cortex has to suppress that. So if you have an upper, motor neuron lesion or some cortical infarct, you might have a reemergence of these primitive reflexes. So it's kind of a similar thing here, is that the red nucleus wants to flex and the cerebral cortex has to say no. So what happens? If I have a lesion below the red nucleus, well, even if you wanted to flex, you couldn't, because the red nucleus can't communicate with your biceps and whatnot. So you're going to have extended arms, extended wrists. However, if you have a decorticate, you're going to have decorticate posturing, a lesion here. So I think if you have a lesion in the cortex versus a lesion around the cerebrum or cerebellum, a little bit more inferior. So if you have a lesion here, you don't have the brain to say, hey, you shouldn't flex, you're going to look stupid. And so the red nucleus is like, I'm going to flex as much as I can. So decorticate versus decerebrate, someone who's rushed into the ER and you see their arms in one position for another, you at least have a little bit of info maybe about where the stroke or the whatever lesion is, where that occurred. All right, so the upper midbrain, as we said, is the only one with nucleus. So you can see two pictures of this on your test, and you should know the upper versus the lower. We have the MLF, which spans the midbrain to the pons, and it kind of makes sense when we think about the lateral gaze pathway, which we need to know. So if we want to look to the left, so our right frontal eye field, FEF, says, hey, we should look to the left because there's something cool over there. There's like a lion we should be aware of. So it'll go, we have all of these dumb crisscross. So it's going to crisscross. The right one goes to the left paramedian pontine reticular formation, which is going to communicate with the left abducens nuclei, which then, so the one that's easy to make sense is the left abducens now is going to go to the left eye and abduct it. And again, we're trying to look to the left. So I do want my left eye to abduct. This makes sense. Now, it's then also, we need to get our right eye to look medially. So continuing on this pathway, the abducens nuclei moves another crisscross, and it moves via the medial longitudinal fasciculus to the oculomotor nucleus back on the right side, and we know that this controls many muscles, one of them being the medial rectus, to have this look medially. If we look laterally here and medially here, the combination of this is we're going to look to the left and see that lion. Now the MLF is super highly myelinated, so I would know that if you have multiple sclerosis, this is one of the first things to go. Previously, we actually didn't really emphasize this. We have the cerebral aqueduct here. This is the interventricular foramen of Monroe, communicating with the lateral ventricles, to the the third ventricle to the fourth ventricle. So maybe that's not the one of Monroe. So the third ventricle to the fourth ventricle. Here we have this cerebral aqueduct, and this is right next to the midbrain. So it's a tiny little amount that we're seeing again right here. As we go a little bit lower, again, we see this little hump, this protuberance. That's the pons. This is where we're going to have the fourth ventricle, and we're going to have a much enlarged enlarged space for the cerebrospinal fluid. So we see that here. There's a large fourth ventricle, a lot of cerebrospinal fluid. So that's a way you can differentiate the midbrain from the pons, the medulla is the small little area for cerebrospinal fluid. So rule of fours, we're going to have the cranial nerve 5, but it's so big it does span. That one's tricky. But then cranial nerve 6, 7, and then 8. 8 is also an asterisk because it's a little bit in the medulla as well. MLF, because again, excuse me, we need to communicate between the cranial nerve 6 and cranial nerve 3 for a lateral gaze. The medial limniscus, again, we have the corticospinal tract for movement, a little bit more anterior. Think of the pre and post central gyrus. And then behind them, we're going to have our MLF and our spinothalamic tract. But again, the medial limniscus, previously known as the dorsal column, will be a little bit more medial. Medulla does not play a role in anger or aggression. That'd kind of be more the amygdala. I don't know where people got that idea from. The medulla, cranial nerve 8, again, it's kind of in medulla and the pons. So cranial nerve 9, 10, 11, and 12, you have this inferior olivary nucleus. It's a little squiggly thing. Mainly, it's just a distinct thing to know, oh, okay, got it, we're the medulla, if you see this on the test. I think this was my test, and I missed it because I'm a dummy. But this is going to communicate with the cerebellum. And then note that we also have the pyramids, which is technically separate, which is, again, anterior is going to be where all of your motor fibers, axons, are going to be in the brainstem. And they desiccate in the lower part of the medulla from the spinal cord. Notice that cranial nerve 9 has a nucleus. So the nucleus is where they're originating from, right? That's where the cell bodies are. And then the cranial nerve itself is, for the most part, where the axons are. This is swallowing. And then it's ambiguous because it's kind of ambiguous. We don't know which one it is. It's in both. It's in both cranial nerve 10. That's probably why it got its name. And it makes sense, though, that they do share some function. They're both for swallowing. We've seen this, and they both have the gag reflex and things like that together. But cranial nerve 10 is actually a very busy boy. It's got the nucleus ambiguous. It's got the nucleus tractus solitarius. It's got the dorsal nucleus, and it's got the spinonucleus, which is randomly some little offshoot from cranial nerve 5, but that one's less important. So the most important, swallowing, visceral information from like what kind of food do we have, what did we just eat, and then the dorsal nucleus for parasympathetic to, hey, like you can start secreting stomach acid. We just had a couple of steaks or something. So here we're seeing all of these things combine to make the vagus nerve just a big bundle of axons. And so maybe one of the most important ones is the NTS, nucleus tractus solitarius, or the nucleus of solitary tract. This is going to pick up if like you have poison in your blood or poison in the food that you just got to eat in your GI. And this is going to send information to an area of your body called the area postrema, also known as the chemoreceptor trigger zone, and say, hey, like we just ate some poison, maybe we should throw up. Maybe that's a good thing to do. So again, there's a debate. The CTZ, I would just say it is. CTZ is the area postrema. They're more or less the same. So mostly we have these tight junctions. So molecules in our blood cannot get access to our brain. But again, this is a double-edged sword, right? Because it protects us, but we also want that information. And so what's going to happen here is sometimes molecules might get in, or they will get in an exposed area postrema, one of our 6 circumventricular organs. And it's exposed because these are toxic molecules. And by getting into this area, it tells us, oh, okay, we should start throwing up because it's binding to this receptor and it's going, uh-oh, this is a toxin. Shit, we just ate some poison. We should throw up. So that's kind of the utility of this. There's a lot of things that go into throwing up. If you're on fear factor, all the things you're seeing and smelling and pain, those nerves are going to go to a vomiting center. We have the NTS, which we said is one of our 4 tracks for the vagus nerve, is picking up the poison that we just drank, Dr. Jones. But then literally there are just things circulating which can interact with the chemoreceptor trigger zone in the area postrema. And then the vestibular system and the labyrinth in our ear. If you're in a roller coaster, it can communicate with the cerebellum, which communicates with the vomiting center. And all of these things together, you can throw up from a roller coaster, you can throw up from eating poison, you can throw up from smelling something you just think is really gross, right? So it's a complex integration of all of these. So the pyramids, we said that there's the crisscross applesauce for your upper, for your cortico-spinal tract for your motor nerves. Same thing as well. You're also going to desiccate in the lower medulla for the medial limniscus dorsal column. And again, we call it this in the spinal cord. We call it this in the brainstem, but it's the same thing. But it should make sense. It's dorsal in the spinal cord, and it's a little bit more medial in the brainstem. So both of these, the motor, so that's 2 out of the 3 important brainstem or spinal cord tracts that we need to know. Decussate in the lower medulla, very important to know. Reticular activating system, also known as the reticular formation, it's going to be in the midbrain, pons, and medulla, and it just helps maintain consciousness. And yeah, so the Rafe nucleus is production of serotonin, also in the midbrain, pons, and medulla. And so just kind of a little bit of a summary. You should be able to eyeball this, right? And there are little things you should notice. This structure is for the midbrain. I mean, and I'm even just coming up with this now. You could just think of like, okay, that's like the beginning of an M. I don't know. That's stupid. But maybe it sticks. Olivary nucleus, boom. I know I'm in the medulla. Also, we see this tiny little cerebral aqueduct. We're probably in the midbrain. We see these larger ones. We know that we're in the pons or the medulla over here. So starting with the medulla, we have the cerebral peduncles. Again, you think of the precentral versus postcentral. In the brain area, the anterior is going to be more for motor movement, and then the posterior is going to be a little bit more for sensory. And we know the dorsal column medial limniscus is going to be, well, you guessed it, medial, because that's the new name. It is now medial. So that is medial to the spinothalamic tract. So proprioception, medial. The pain temperature, it's a little bit more lateral. Now we have a red nucleus if we're in the upper one. We have the substantia nigra compacta, which is going to be dark. We have the tegmentum over here, the VTA to the mesolimbic and mesocortical pathway. We have the tectum, C for colliculi, because we have a superior colliculi for light, inferior colliculi for sound. Cranial nerves 3 and 4 are midline because they're evenly divisible by 12. Then we're moving into the pons, where you can see, again, anterior corticospinal tract. A little bit more posterior, we're going to have the sensory ones, and this one is going to be M for medial. And the same thing over here. We have our pyramids where decussation happens in the lower medulla, and then we have the, again, medial for the proprioception, and then we have the spinothalamic tract over here. Again, they're the posterior versus anterior, precentral, postcentral. Very useful way to think about it. This is actually, I think, pretty high yield. It's super dumb. I think it's ridiculous we have to know this, but I would know it. Okay, the cerebellum is important for kind of sort of like the basal ganglia. It helps fine-tune and coordinate movements, but it's also important as it is this like central point of integration for balance. So, you know, you can get severe vertigo and ataxia if it's defective. So it's going to integrate kind of these 3 inputs, things from the vestibular system, things from the proprioceptive system, and things from the visual system to help keep, you know, your posture intact. So I kind of went on a crazy photo shoot. So we're going to fly through all of these dumb photos that I took, but maybe it'll help just, for me, it was always confusing just to understand the geography of everything. But cerebellum means little brain, and it kind of is like a little brain just south of the tentorium cerebelli that we see right here. So it's infratentorial, and there it is. So it's got a posterior lobe. We'll get into it. So here's the posterior lobe right here. Mental snapshot. Here's the vermis in the midline. Mental snapshot. Here are the tonsils. The tonsils here, this is what can herniate if you have a Chiari type 1. And if you have Chiari type 2, which is more severe, you might also have the vermis shown here also herniate. In other words, squeeze through this foramen magnum that we're looking at. And we see these longitudinal striations, and we know that is the medulla. All right, so the anterior lobe now, again, I guess it's peaking a little bit above the tentorial layer, but mostly it is infratentorial. So we just remove this, kaboom. We're now looking at the anterior lobe, which we haven't seen yet. And again, here you have the vermis. Here you're going to have the tonsils. Here you're going to have the posterior lobe. And now there's this nice division, this horizontal fissure here and this primary fissure to just demarcate different landmarks. Again, we're looking at the vermis. Excuse all these dumb photos. Looking at the anterior lobe. We're looking at the posterior lobe. Notice how big the posterior lobe is compared to the anterior lobe. And the flocculonodular lobe, which is hard to actually see, but it plays a really important role in balance and integration of visual and vestibular inputs to help keep you from falling over. So it's going to be important for things like the Romberg test. So dumb little video, but we have 3 different peduncles which are going to attach the brainstem to the cerebellum. The inferior and the middle one have to do with afferent input. So information is coming in, you can imagine coming in from the eyes, coming in from the vestibular system, coming in from proprioceptive, from the dorsal column, medial lemniscus. And then the efferent is going to be from the superior part, which goes through the midbrain and up to the cortex and says, hey, let's try to coordinate our movement in an XYZ manner. So that's the inferior. Oh, gosh. Did it even work? Nah, I don't care. All right, that's inferior, that's middle, and that's superior. You get the idea. All right, so again, proprioception, vestibular, sight is coming in from the bottom, in from the middle. It's getting processed, and then it goes out through the superior cerebellar peduncle. And here's another dumb video. I think I was just too proud that I understood it. So we're highlighting right now the superior cerebellar peduncle hidden right there. And let's see what happens. Okay, then there's the middle one. There's the vermis in the midline. There's the anterior lobe. And then there's the posterior lobe. And there's the flocculonodular lobe. Again, posterior, vermis, tonsils, medulla. We can see all of these nice longitudinal striations. The pons, the big fat pons. Sounds like a nickname for your, if you got a big pot belly, you got your pons. And it's kind of sticking out like that. And then our pituitary with the infundibular stalk. Arbor vitae, because if you look at this from a sagittal slice, this looks kind of like a tree here a little bit, right? And of course, this is our third ventricle. This is our fourth ventricle, interventricular foramen of Monroe. We have the lateral apertures and the medial apertures of Magdapi and Lushinka or whatever. I don't understand this as well as I probably should have. So take what's about it, go on with a grain of salt. But I think more or less this is what's happening. Maybe getting a detail wrong, and definitely leaving out a few details. But we have these inputs coming in. So they come in. They rest at this little nucleus right here. We have the dentate, the emboliform, and others, which we'll get to. And so they're going to come here, and then they're going to branch out. They're going to get processed. That processing goes back to the nucleus, maybe gets processed a little bit more, goes out, and then that becomes the efferent to the brain. That's my dumb understanding. There's definitely a lot more to it with Purkinje fibers and Mossy fibers and whatnot. There's another little simplification of it. All right, so here are the ones we were talking about. We have the dentate, the emboliform, the fastigial, and the globose nucleus. And so people remember this is don't eat greasy foods. That's moving from the lateral to the medial. And the eat greasy sometimes are called the interposed nuclei, the ones in the middle. So we've mentioned this as the anterior, as the posterior, the big one, and the flocculonodular lobe. We kind of have a vermis in the midline and the tonsils in the midline of the posterior section. But another maybe more common way is to think of this as the spinocerebellum, which is really just the vermis for the most part, the vestibulocerebellum, which is really just the flocculonodular lobe, and the cerebrocerebellum, which is really just the lateral parts of the cerebellum. And that would include here what we're seeing with the posterior lobe, the large one, and a little bit the anterior lobe, well as here. So notice the spinocerebellum is going to pick up a little bit of the, the posterior and the cerebellum as well. But this is probably a better physiological way of thinking through it. So the spinocerebellum is for properly executing coordinated movement. So this is something that's actively occurring, right? Like I'm walking down the street, and my cerebellum is helping input each of my steps so that I don't look silly and trip. It's using largely proprioceptive information from the dorsal column medial lemniscus and the spinocerebellar tract to achieve this. So that is the central midline. And so that would be kind of like that would be the interposed nucleus, but especially the fastigial nucleus. Don't eat greasy foods. Eat and greasy are the interposed. Then we have the lateral parts. Again, this is posterior and anterior. The lateral parts for planning coordinated movements. So if I want to, do a wicked serve in tennis, the cerebrocerebellum here, the lateral parts of the cerebellum are going to help me execute this function as well as I can, which is not that well. And then the vestibulocerebellum is kind of in the name. Vestibular has to do with balance, right, from the ears. And this is just really the flocculonodular lobe. And this is going to be mostly the, this is really just coordination and balance. So a little bit of a link here with this as well. And this is going to receive balance information from the semicircular canals, the vestibular nuclei, and the superior colliculi and the medial visual system, basically, right? And we said that there are 1, 2, 3 things for balance, and they are going to be the proprioception. We have that over here, and then we have the vision and the vestibular system over here. Okay, so we've gone all the way from the tippy top of the brain, the cortex, through the subcortical structures, the brainstem, cerebellum. Last stop is the spinal cord before we get into the vasculature and the veins and the ventricles and whatnot. So we have the spinal cord, which moves down through the vertebral foramen, and it's going to shoot off little nerve roots through the intervertebral foramen, where they're going to have these large discs, which are going to cushion on the either side of a vertebral body. Also just note that there are 7 cervical vertebrae, 12 thoracic vertebrae, 5 lumbar vertebrae, and then 5 sacral vertebrae. And it's all matched with nerve roots. So we're going to see 12, 5, 5, except for the cervical, where there are 8 cervical nerve roots. That is going to be really important when we're trying to see whether a nerve root goes above or below a particular level. And that's going to be important for herniations. If we're looking, let's say that we have our little disc here, so between C1 and C2, always above the disc, it's going to be the nerve root above. So here's the C1, C2, the nerve root is moving above the C1. And then the C2 nerve root is moving above the C2 vertebrae, et cetera, et cetera, et cetera. Except that for the fact that, again, that we have this mismatch, now the 8th nerve root has to go below. And if that goes below, then that means that everything after that is also going to go below. So if we're looking at like the T1 vertebra, the T1 nerve root is going to be below. And if the L1 vertebra, it's the L1 nerve root is going to go below. So if that didn't make sense, just memorize that the cervical nerve roots will always exit above their corresponding vertebrae and discs. And then for the thoracic and lumbar, it's going to be below. So actually, let's skip here. I think I moved this out of order. So the point of that then is that if I had a herniation between C6 and C7, so the nerve root here is going to project laterally and just right next to the disc. So if I have a herniation, remember this is the C7 vertebra, the nerve root that it corresponds with it exits above. So this is the C7 nerve root. I don't know what size C6, C7 nerve root. That is going to, this herniation between C6 and C7 is going to affect the C7. So C6 and C7 herniation, we see that it affects the 7. Now, what about here? Here, I'm going to have the L4, L5 disc. And now, again, once we go to the thoracic and lumbar, the nerve roots exit below. So here's the L4 vertebra. So the L4 nerve root goes below. And here's the L5, and the L5 is going to go below. But another thing happens to kind of offset this because, right, we might now conclude that it's the L4 nerve root that's being affected. But because of the way the cauda equina works and the nerve roots kind of, I don't know the right metaphor. They're procrastinating and they have to play catch up, but they start to descend actually quite inferior before moving laterally, right? Here it's just kind of moving right laterally, but here they move really inferior before moving laterally. So if we have a herniation, it's actually not going to hit the L4 nerve root. It's actually going to hit the L5 nerve root. So again, if we look L4, L5, it's actually going to go 5. So if that was all gobbledygook, what you should know is that whenever you're looking at a particular disc herniation, it is always going to be with a more inferior associated vertebral body or vertebral root, or nerve root, however you want to think of that. So the L5, between the L4 and the L5, and then between the C6 and the C7, it's going to be the C7. So dermatomes and myotomes, all of these nerve roots that are exiting are innervating different parts of the body. Dermatome is talking about the sensory aspect, and the myotome is talking about the motor aspect. For the most part, though, these kind of line up. And you guys don't have to be experts, but you should have like a decent rule of thumb. So let's start with C5 at the shoulder, and then we're going to move down more or less C6, C7, C8, and then all the way up here T1. I don't know why there's another T1 there. So T1 up here, and then T10 at the belly button, T10. And here we're looking at L1 kind of at the trouser and the medial side. And as it moves down the leg, L2, L3, L4, and L5, it's going to kind of move medial to lateral as well, is what these arrows are trying to show. This is also on the anterior for the lumbar. The sacral is actually going to pick up more on the posterior aspect. And it's going to move up until it then it's going to supply the bathing suit region, the genitals, and the perianal region and whatnot. So a couple landmarks, C5 to C8 for the arms, T1 to T10 for the thorax, L1 to L5 for the anterior leg, and then S for the posterior leg and the genitals. Now, a couple of reflexes you should know, C6 with the triceps, biceps, C7, cremaster reflex right here, L1, kind of makes sense. That's sort of where they're being stroked. I don't know the right word. Patellar, I think L1 to L5, what's in the middle? The middle is L3. What about what's in the middle of your leg on the anterior side? It's your knee. So that's why this is the patellar reflex. Achilles, right when we go into the back side. So again, we've been kind of going like medial to lateral on the anterior, and then we go pick up on the posterior. So the very first thing then would be the S1. They say S2, S3, S4 keeps the penis off the floor. And then also winks galore. So knowing the associations there is good. Also point and shoot. So point and shoot. Parasympathetic and sympathetic. The erection point is parasympathetic innervation. Sympathetic shoot is going to be, well, just there, the sympathetic innervation. All right, so sensory neurons are going to move up. Motor neurons are going to move down. The sensory neurons, though they're going to enter the spinal cord on the dorsal side, the motor neurons are going to exit the spinal cord on the ventral side. The associated soma, the cell body for the sensory is going to be the dorsal ganglion line over here, and for the motors, it's going to be in the ventral horn located right there. So if we're looking at this, remember that the white matter is on the outside and the gray matter is on the inside when in the spinal cord. If you're thinking about what's going on in the cervical, let's just pretend we're talking about innervation of muscles. Let's look at three, so let's think about axon tracts, white matter. So going through the cervical, I might have one axon that is ultimately going to supply the arms, one axon that's going to supply the abs, one axon that's going to supply the legs. When I get to the thoracic, now it's just one axon for the abs and one axon for the legs. And when we get to the lumbar, it's just one axon for the legs. So what do we see? We see that we're losing white matter as we go down, right? Because we don't need as many axon tracts. So there's very, very little axon tracts here because we just need them for the legs. Maybe a little bit more here, a little bit more here because it's the legs and the torso. And here we got a whole bunch because it's the legs, the torso, the arms. All the axon tracts have to go through the cervical layer. So you should be able to identify that just based on the white matter alone. Additionally, we're going to have this little lateral projection in the thoracic region for the lateral horn for the sympathetic nervous system. All right, so there's a lot going on here, and it's actually much more complicated than even this picture shows, but we just need to know about these. The corticospinal, dorsal column, and then the spinothalamic tract. So the corticospinal is going to be a motor. Motor is descending. Dorsal column is dorsal column in the spinal cord, so that's what I'm going to call it for now. But remember that it's called the medial lemniscus when we get into the brainstem. And the names are kind of fitting here. Dorsal column, it's going to be dorsal in the spinal cord. It's going to be medial in the brainstem. So this is for proprioception, like knowing where your body is in space, and fine discriminatory touch, right? Like reading Braille or something like that, right? You can really, really fine-tune and precisely tell one little bump from the other. And this is going to be ascending because it's sensory. This is also ascending. I don't know why it says descending because these two are sensory. This one's going to be a little bit more primitive though. Crude touch, pain, temperature. How do we remember these? I always thought like cortico, like the brain. The brain is like initiating all of these complex like muscular movements. Like we talked about the basal ganglia, right? Like Robert Baratheon, the king. He is saying, I want to scratch my nose. I'm itchy, right? So we're planning the movements. So a lot of thought goes into the muscle movements, and that's the dumb way that I remember it, at least. Dorsal column, I think of like dorsal fin is a dolphin. What are dolphins? They're really smart, they're really evolved, really enhanced. So they have this sophisticated proprioception and fine discriminatory touch. Again, it's a little silly, it's how I remember it. And then the spinothalamic tract, I always thought of the spine. If you injure your spine, yeah, it's true, you can't move your muscles. But the first thing you always see in movies is someone gets in an injury in war and they don't go, oh no, I can't move my hand. They go, I can't feel my hand. I can't feel my leg. So that's at least how I remember that the spinothalamic has to do with like just sensory, just basic senses, like feeling something, pain, temperature. Yeah, fun. All right, so some decussations to know. Corticospinal is decussating at the medulla, at the lower medulla. Not all of them technically. So most of the motor tracts are going to go to the arms, legs, abs, things like that. But we do have some motor tracts that are going to the face, and the face is going to be above the medulla. So they technically don't, they do decussate, right? Here's the right motor cortex. Everything is going to the left side of the body, but they're not decussating at the medulla. They're decussating, I don't know, somewhere else. I would know that all of the motor innervation is going to be the bulbar group when we are talking about like facial muscle innervation, bulbar. All right, so it's a 2 neuron tract for the corticospinal tract. So anything from the cortex down to the cell bodies in the ventral horn is going to be upper motor neuron, and anything from the ventral horn down to the muscle is going to be the lower motor neuron. And that's going to be really important for pathology later. And not everything is somatic, right? Like I'm flexing my bicep. Some of it's like visceral, like I need to do peristalsis and I need to, cause the smooth muscle to, contract or relax or something. The dorsal column is similar to corticospinal in that it also decussates at the lower medulla. There's also a difference between, there's 2 different tracts technically that make up the dorsal column. The nucleus cuneatus, which is for the arms, and the nucleus gracilis. I always thought, if you know about Gracie Jiu-Jitsu is all about like using your legs more than probably moving your arms. And so I think of gracilis, Gracie Jiu-Jitsu, legs. Now is the spinothalamic, right? Spine, basic, can't feel my legs, baba, is pain, temperature. This is actually going to decussate at the right when it comes into the spinal cord through the dorsal aspect of the spinal cord. It's going to decussate and then ascend on the contralateral side. Actually, that's not always true. Sometimes it does do that, but there's actually something called Lissauer's tract. So that, here's my spinothalamic nerve coming in. Instead of decussating right here, it actually might go up 1 or 2 levels. It can technically go down. It can descend 1 or 2 levels and then cross and then move upwards on the contralateral side. So this is going to be important when we get to things like Brown-Séquard syndrome and whatnot. So a little summary. Corticospinal tract, I think of cortical, brain, plan movements. This is decussating at the medulla. Don't worry about this. Worry about this. Knowing where these are. These are kind of on the posterior side, and this is kind of on the anterior side. This is going to be important for when we talk about strokes and whatnot. Looking at the dorsal column, you think of dorsal fin, dolphin, fine touch, proprioception. It's very smart, and this is also decussating like this at the medulla. And then we have the spinothalamic spine. I can't feel my spine. I can't feel my legs. Pain, temperature. This is very basic things. This is technically decussating at the vertebral level where it enters, or it can go through the Lissauer's tract and go up 1 or 2 and then decussate, which is going to be important. Also, Gracie Jiu-Jitsu is for the legs because you have the cuneatus for arms and the gracilis for the legs in the dorsal column. Okay, cool. We made it. Whew. Now we can do a hard pivot to the arterial vasculature of the central nervous system. This is, strokes, just in terms of like clinical relevance, strokes of, the first or the 4th leading cause of death, depending on how you look at them. And even if death isn't an issue, it's still like a tremendous quality of life impact. And so it's just a tremendous burden on our healthcare system. It's really important we understand strokes. Also very highly tested. But to understand strokes, it really helps if you understand the basic geography of everything. So I'm a nerd. We've been through this, but like one last example. I watched Game of Thrones. It was amazing. My girlfriend had never watched Game of Thrones, so I rewatched the whole thing with her. And she was having trouble, or maybe I was just being a little bit too like paternalistic and demanding. Maybe she was having trouble following, and so I bought a blackboard wallpaper and put it up in my living room. All my roommates hated it. It was a huge eyesore. And so every time we'd watch, I would draw a map of Westeros and Essos, Eastros, so that we could know where everything was and kind of like map out the battles and where King's Landing was relative to everything. It's probably super annoying, and she probably put up with it because she liked me. But like, yeah, I would make the argument that it made the show a lot easier to follow if you kind of knew where everything was. Same thing with strokes. If you know where the arteries are, it's easier to figure out like the immediate proximity of what's going to be affected. So without further ado, let's get into it. So We have anterior circulation of the brain with the ICA, and then we have the posterior circulation of the brain with the vertebrobasilar artery. This is kind of what the whole picture is going to look like, and we're gonna build up everything, and it's hopefully all going to come together. So here's the ICAs. The vertebral arteries are going to again combine to the basilar. So this is going to be the posterior aspect, and this is going to be the anterior aspect. So let's watch this fun little movie. Again, just keep in mind the carotids are going to be the anterior side, and the vertebral is going to go to the posterior side, where they eventually converge to make the basilar. So we're starting in the aortic arch. And we have the brachiocephalic over here on the left, immediately the common carotid to the anterior portion, subclavian real quick, followed by the vertebral. All right, here's the subclavian to the vertebral, and the common carotid here is actually just coming straight off the aortic arch. I don't think that's that important. Main takeaway is this. Okay, so the common carotids are going to branch to form the external carotid artery, which is going to supply the face, and the internal carotid, which is the one important for our purposes, to supply the brain. And then the vertebral arteries in the posterior aspect, and here kind of on the medial side that we're looking at, it's going to penetrate through the transverse foramen of these cervical vertebrae. So let's watch another fun little movie. I thought of it as like threading the needle when you're trying to like get through these tiny little foramen. Common carotid, external, as promised, internal, and boom, carotid sinus for the glossopharyngeal nerve, and then the vertebral. Cool. Lateral below the head, you don't want to get here. This is where we have our middle meningeal artery. If this ruptures, you get epidermal hematoma, which is not a good thing. It comes off of the maxillary artery, which is itself a branch of the external carotid. So let's take a look. So we're starting here. So here's the internal, here's the vertebral, and right now we're highlighting the external. Let's take a look. External goes to maxillary. Maxillary goes to middle meningeal. We're taking away, remember there's two dural layers. We're taking the cranial dural layer. Right under that is the meningeal dural layer. And that is where we have our middle meningeal artery. So if you had this rupture, it is still technically outside the dural layer, hence epidural. It's outside the meningeal dural layer, which is the important one. Now the internal carotid is going to enter the brain through the carotid canal. But it actually has a really complicated trajectory as it moves up. So it goes through the carotid canal. It's going to make a hard, like 90-degree turn or 70-degree turn or whatever. It's going to start moving like medially rather than superiorly. Let's get it from another picture. So same thing. So you can kind of see it over here, right? It's going up and then it kind of just takes a sharp turn. Here, boom, right? So it's coming in through here and then suddenly it's traveling this way. And we see that again here. It's going here, goes here, and then it goes right up again. So right when it pokes its head up like a groundhog on Groundhog's Day, it's going to poke its head up right into the cavernous sinus. And this is kind of interesting. This is the only time like an artery is ever like in a venous structure. So that's kind of interesting. The cavernous sinus is interesting in general just because we have a lot of like ophthalmic nerve and the oculomotor nerve and the trochlear nerve and whatnot are moving through it. So it moves up through that. And there we go. That's a fun little ghosting picture. Okay, enough of that. Meanwhile, in the Legion of Doom, so the vertebral columns are now on the posterior side. We've threaded the needle through the transverse foramen of the cervical vertebrae, and now they are moving up through the foramen magnum. Very cool. And all right, so once they get a little bit higher, we're going to have this offshoot. And this is going to be the anterior spinal artery, which supplies the medial medulla. Not shown, but it supplies the medial medulla. You can see that over here. And that is going to supply the anterior, as the name implies, anterior spinal artery is supplying the anterior spinal cord. What tract is there that's relevant? We're dealing with the spinothalamic tract is going to be the relevant one. Right before they merge into the basilar artery, they are going to have offshoots, which are the posterior inferior cerebellar artery. This is really highly prone to strokes. It's going to be Wallenberg syndrome, which we'll talk about. So again, pica is going to be the part of the cerebellum, but also more importantly, the lateral medulla. All right, so now we go. Hooray! They've joined. Union. They've merged as one. Right? It's a beautiful ceremony. Now we have the basilar. Right after that, we have another thing. So we have the pica, then it became the basilar. Now it's the AICA, anterior inferior cerebellar artery. It's going to supply a little bit more superior on the cerebellum, but it's going to supply more importantly, the lateral pons, lateral pons. Where we continue up, we have the basilar artery, and then shooting off the basal artery are the pontine arteries. And so here we have the basilar artery, and here we have the pontine artery. So they're both going to be supplying like the medial pons for the most part. And again, this geography is really important so that you can identify what the stroke symptoms will be. I always thought that this kind of looked like the little face hugger thing from the Alien movies. So I looked up SCA. SCA, there are so few strokes of the SCA that when I Googled it, I could not find a good picture. This was like the best picture I found. And that just kind of underscores like this isn't that important of one. I think it looks like it was drawn with an etchy sketch, but this is mostly just implying the cerebellum, really not any of the brainstem structures. And this is just more fun cerebellum hot pics. There's a cerebellum. There's a cerebellum from another angle. Beautiful. Being supplied by the SCA, AICA, and PICA. PICA, AICA, SCA. All right, so now at the end of the basilar artery, we're going to have the PCAs, posterior cerebral artery, branching off. These are going to supply the occipital lobe, which is important for vision. They're also going to supply the midbrain, the entire midbrain, the medial and the lateral aspect. Note, though, and we're going to come back to this, that the occipital lobe has also is vasculature from the middle cerebral artery. So it's got a dual supply, at least the part of the occipital lobe that supplies the central or macular vision. So if you have a PCA stroke or an MCA stroke, the central vision will probably be spared. It's probably an evolutionary thing because it's just such an important thing to have central vision that, maybe evolution naturally selected for people whose arterial blood supply like kind of overlapped, right? There's a Venn diagram of the MCA and PCA for the macular region. Anywho, so now we're looking at the PCA, and we have these posterior communicating arteries branching off of this. The posterior communicating, anytime we see it communicating, there's very high likelihood that we might see a bari or saccular aneurysm there. If these bust, we get these subarachnoid hemorrhages, and at the posterior cerebral artery, this is going to be right around the superior aspect of the pons, the superior aspect of the midbrain. We know that cranial nerve 3 is hanging out. So in other words, if you have a bari aneurysm of the PCOM, it could damage cranial nerve 3, and you'll have this down and out pupil. Probably with constricted pupils, down and out eye with constricted pupils. All right, return of the internal carotid artery. We did the posterior. We're back to the anterior. Let's see what's going on. So, the ACA, anterior cerebral artery, is going to branch off from the internal carotid, and there's going to be, see that little. There's a little tiny anterior communicating artery between them. The communicating arteries is all about like collateral blood flow, right? If there's an infarction over here, well, that's okay. Like maybe some of this blood flow can be diverted over there and then make its way back over there. So a lot of collateral blood flow. And again, we have another place where we could have a bari aneurysm. What could be compressed now? Well, this is the sella turcica. That's where the pituitary goes, and that is near the optic chiasm. So you could get a bitemporal vision loss, which we'll get into. And then the MCA, which is probably the most important artery. This is the most common stroke site, and this is going to be you're going to have contralateral loss of the arms and face. So you could also have a bari aneurysm here in addition to the MCA just having an ischemic, embolic, hemorrhagic, whatever type stroke. And again, so this whole thing is the circle of Willis. Circle is supposed to be a circle like that. I think it looks a little bit more like a cyclopentane, but it's all about collateral flow, so that if there's kind of an infarction or hemorrhagic incident in one part, the blood can be redistributed to try to save as much brain tissue as possible from an ischemic death. And so, okay, we had ADCOM, PCOM, and also the MCAs where we might see these bari aneurysms. This one is the optic chiasm because we see that's where the pituitary is. Just, and it's going to be, I'm just trying to stress this because it's really high yield to know about pituitary tumors and compressing in the eye, optic chiasm. And then the PCOM is going to, as we said, could damage cranial nerve 3, the oculomotor nerve. Remember that there is the cranial nerve 3 is on the inside and the PNS is on the outside. So ischemia would deprive cranial nerve 3 before the parasympathetic nervous system, and a tumor is going to damage the parasympathetic nervous system before it gets cranial nerve 3. But it could easily get both. It often will get both. There we go. Here's this beautiful animation that I made, and another beautiful animation at the PCOMs getting the optic chiasm and the oculomotor. You can see it right there. All right, so the MCA has these tiny little branches that feed deep into the subcortical regions of the basal ganglia, and these are particularly prone to susceptible to damage from hypertension. So if you have hypertension, you get an ischemic stroke. The hypertension, you know, and other things as well, like lipohyalinosis and microatheromas, are going to lead to these lacunar infarcts. A lacunar infarct for lenticular striate ischemic stroke. And then an aneurysm from a Charcot-Bouchard is also associated with hypertension. So very much hypertension with a lenticular striate, which is a branch of the MCA, which supplies the basal ganglia. ACA is going to go right here above the corpus callosum. Right there above the corpus callosum, it's easy. MCA is going to go right along this little sylvian fissure, this lateral fissure, and supply the lateral. It's going to apply a slightly larger region, but for the most part, just the lateral side of the brain, of the cortex. We can see it there, and we can see it there. Again, that's all MCA right there. Okay, so this is important when we think about the MCA and ACA when we think about this with regards to the homunculus. So remember that the medial portion is going to be the legs, and the lateral portion is going to be more the face and upper extremities. So if we look at this, the ACA right here is the medial portion, and that gets everything here, which is going to be a bunch of kind of leg structures. And then we get the MCA, which is going to be on the lateral side. That is what it's supplying. And that's going to be more of the face and the arms and fingers and whatnot. Okay, so we're looking at the PCA, right? So this is the PCA. We said it supplies the entire midbrain, both the lateral and medial part, but it's also, and probably most importantly, supplying the occipital lobe. But again, this region right here, which is where we might have the the part of the occipital lobe that processes the macular vision, has some coming from the posterior cerebral artery, but also a little bit coming from the middle cerebral artery. There is this, right here, there's a little bit of collateral circulation there. Maybe not collateral circulation, I don't know if that's the right term, but it can feed from the left artery to the right artery, right? So if there's an infarct in one, it's going to be spared usually. All right, this is a really great summary. I love this picture. So I did not make this. So the vertebral arteries coming out from the posterior side are going to make the anterior spinal artery, which gets the anterior part of the spine, but it gets the medial medulla. The pica and the aeca, these are both going to be lateral, so I'll just commit that to memory. So it's going to be, the pica is going to be the lateral medulla, and the aeca, medulla always means like deepest, right? When you look at cortex, always means the outside of medulla, always means deepest in anatomy. So it's always know that the medulla is the deepest. So pica is going to be the medulla. Aeca is going to be the lateral pons. The basal artery and the pontine arteries, the little face hugger thing, is going to be the medial pons. The SCA doesn't really do much. It's the cerebellum. These are all technically cerebellum, so I would know that. The SCA very rarely strokes, hence that etch-a-sketch picture we saw. PCA is going to be the medial and lateral midbrain. MCA is going to be the lateral cortex, which is going to be the face and the arms, and the ACA is going to be right above the corpus callosum, which just gets the medial cortex, which is going to be the legs of the homunculus. This is really just a picture. This is a more complicated but more more accurate depiction of how everything looks and how everything's arranged. I would be very familiar with it. One thing we didn't talk about is that the ophthalmic artery, which becomes the retinal artery, comes right off of the internal carotid artery. Okay, now that we've talked about the arteries, it seems only fitting that we would then talk about the veins. But when it comes to the brain, it's difficult to talk about the brains without also talking about the meninges and the ventricles. As we'll see in a couple minutes, it's all very interconnected. So let's actually start with the meninges before we then get into the ventricles, and then finally the veins, and we'll see why we're doing it in this order. So the meninges is really just the dura mater, dura as in durable. This is the thickest of the meninges, followed by the arachnoid layer. And under the arachnoid layer, we have this subarachnoid space. Kind of looks like spider webs, I think, hence the name arachnoid. And this is where the cerebrospinal fluid is actually going to sit most of the time. And then we have the pia mater, which tightly hugs the brain. The arachnoid and the pia together are the leptomeninges. Now, when we do talk about the dura, though, it is important to make a distinction. We have the periosteal, also known as cranial dura, and then the deeper meningeal layer. And then there's going to be important distinction between those two when we're looking at divisions of the brain. So one more note on the subarachnoid space. This is where we might administer medications. We might also extract cerebrospinal fluid from here for analysis. All right, let's watch this amazing video. So periosteal cranial dura, meningeal cranial dura, arachnoid cranial dura, and then the pia not shown. We already saw that. I could have done without that. Oh well. All right, so notice here we have the cranial dura. Named cranial dura because it tightly hugs the cranium, right? Go around this entire thing. Is there ever a moment where the cranial dura is not touching the skull? No, it's always touching the skull. Now, usually it's also on the other side touching its brother, the meningeal dura, right? The meningeal dura right here. However, we have these natural divisions of the brain, completely natural, right? We have a right hemisphere and a left hemisphere. They are distinct. And we also have a cerebellum. And based on that, if we keep in line with the logic that the meningeal dura always hugs the brain and the periosteal or cranial dura always hugs the skull, what's going to happen is during these natural divisions, the meningeal dura is going to go this way and the cranial dura is going to go this way. And it's going to create these little pockets. These little pockets are the sinuses. This is where we're going to have a lot of our venous system basically dump into. This is going to be venous blood. It's just kind of like sitting there. It's not really directional flow, which is kind of weird. Now, during these separations, this little area here is actually shown a little bit more closely here. These are known as cerebelli or cerebri, but this is where we're seeing the pia matter and the arachnoid matter and the meningeal dura all sort of coming together. Again, completely natural division of the brain. We mentioned the subarachnoid space contains cerebral spinal fluid. The purpose is to feed the tissue, to remove waste from the tissue, and to cushion the very delicate brain. I would also note that the subarachnoid space containing the cerebrospinal fluid ultimately is going to dump into these sinuses. A lot of things are going to just dump into these sinuses. So they're going to dump in through these little holes called arachnoid granulations, which we can see a little bit better right here, right? So they kind of look like these little alveoli. So here's my little spider web. So that must be the subarachnoid space with all the cerebrospinal fluid. It's going to come in here, and we can actually kind of see it a little bit better over here, right? It's going to come in here, and the cerebrospinal fluid is just going to leak out into this little cavity, this natural cavity, which is a sinus, which is a natural consequence of the separation of cranial and cranial and meningeal dura. So the CSF is going to go here, and then it's ultimately going to be dumped out, which we'll get to. So going back to the natural divisions of the brain, so we said the cerebelli and the cerebri, and it's called tentorium. But this is just the natural, right? If we think about this, this is where your right hemisphere of your brain would go, and the other side is going to be the left hemisphere of the brain. They're separate things, and because they're separate, we have some meningeal layers that tightly hug each of them. We get this natural falx cerebri, dura matter. There's technically also going to be pia matter and arachnoid, but the main thing is probably the dura matter in here. And then we have the tentorium cerebelli down here. So this separates the left and right side of the brain, and this is going to be separating the, this is the supratentorial, infratentorial, in other words, like the brainstem and the cerebellum from the basal ganglia, limbic system, cortex, etc., the cerebrum. So again, just in case you're, in the small chance you're not sick of it, let's look at this again. So a couple different ways this can cut. Falx cerebri right there, tentorium cerebelli right there, and then the falx cerebelli right there. So these natural divisions of the brain, this is just the separation of our two dura layers. Again, you have this, it's named after, like, falx is like a sickle, and it kind of looks like a sickle a little bit. I kind of buy it. This is the little sickle. Okay, everything is ultimately going to be dumping in to this dural system. So let's go ahead and take a look at these. So we're highlighting the falx cerebri right here, and now we're transitioning to superior sagittal sinus, inferior sagittal sinus right next to the corpus callosum, transverse because moving the transverse direction, sigmoid because it's sigmoidal, it's curving, cavernous sinus important, and it all dumps into the internal jugular vein. That's how we're kind of getting rid of everything, right? The veins dump into the sinuses. The CSF dumps into the sinuses. The sinuses eventually are going to dump into the internal jugular vein, which takes it away to the rest of the body. Cavernous sinuses, very important. So it's going to contain a lot of really important structures. A lot of structures related to innervation of the eye. The cranial nerve 3, cranial nerve 4, cranial nerve So the ones I highlighted are the ones that are kind of odd. This one is odd because it's out of order, right? This should be 3, 4, V1 and V2. That order makes sense. So this is out of order, the abducens. But it is still there. You need to know it. Now, the next point is that this is kind of out because this is eyes, this is eyes, this is eyes, this is eyes, and this is not eyes. That's like the sensation of my nose. So I don't know. For me, I kind of remember everything goes in order and everything has to do with the eyes except for those two exceptions, and that kind of helps me. Remember that we also have this weird trajectory of the internal carotid, which makes its way through the cavernous sinus. And then right in between the cavernous sinus. So here's our cavernous, here's our cavernous sinus and here's our cavernous sinus, and then they're interconnected like right here. And so this is the cavernous sinus of one side, this is the cavernous sinus of the other side. And again, right in the middle here, we have our pituitary. And then above that is of course going to be the optic chiasm. So the ventricular systems of the brain kind of looks like a ram, lateral ventricles 1 and 2. Then we're going to have the third ventricle and then the fourth ventricle down here. Connecting them is going to be the interventricular foramen, also known as the foramen of Monroe, and then connecting the third and fourth, kind of behind this, deep to that structure, is going to be the Sylvian aqueduct, also known as the mesencephalic aqueduct. So within the ventricles, we have the choroid plexus, which contains ependymal cells, which generate the cerebrospinal fluid. And so if we follow this again, we're highlighting right now ventricles, the left lateral ventricle, so 1 or 2, order doesn't matter. And it is going to go via the interventricular foramen of Monroe to the third ventricle, which goes through the cerebral aqueduct, or the aqueduct of Sylvius, to the fourth ventricle, which goes to the lateral, which goes to the median aperture. Note that the lateral aperture is the Luschka, I think of L for L, and then the median aperture, a median for Magendie. And where does all of this go? It's going to go to the subarachnoid layer and the cerebrospinal fluid, and it's ultimately then going to dump back into the venous sinuses. So this is just a great picture, kind of overlaying the flow of the cerebrospinal fluid. Okay, so the venous sinuses don't actually have directional flow, and unlike the veins, which do have directional flow. And then again, their job is to collect CSF, but also they're collecting all of the stuff from the veins. We have a picture. Is there a picture? Am I frozen? Nope. There we go. All right, I ruined it. All right, can I go back? There we go. Okay, get ready for the picture now. Boom, all the veins drain into that, into the sinus, and then the sinus itself is eventually going to drain into the jugular. And the emissary veins, I think of like emissary as like you're taking an important message from like one nation to another, and this is going from outside of the skull to beneath the skull. So that's quite a it's quite a mission. It's quite a long journey. It's quite different landscapes and geographies if you think about it. If you get a cut to your head though, this could be quite bad because infectious agents could travel through the emissary veins and get into the skull where they can then feast on the brain, and that's not good for you. And here's a silly video. Yeah, so again, it's draining from the scalp through the skull, and it also is going to dump into the sinuses. Poor sinuses, they're taking everyone's garbage. We then have these bridging veins. So the emissary veins go from the scalp beneath the skull to the sinuses. These are going from the cortex, the actual brain parenchyma, through the arachnoid layer, through the dural layer, and then into the sinuses. So they're bridging from the brain to the sinuses, hence the name. Well, if you get a rupture there, so again, this is our spider web, so this is the subarachnoid layer, it typically actually breaks and fills the subdural layer. So we saw the middle meningeal artery off the maxillary artery off of the carotid artery is going to be the epidural. This is going to be a subdural. So it's a subdural injury, and we see this in alcoholics and elderly people and babies. Woo, okay, last section, then we're in the clear. Okay, another pivot. We're going to be talking about cells here. So another pop science thing. Some people say that we only use 10% of our brain. Is this true? No, of course, this is completely ridiculous. Definitely not true. For one, if I only use 10% of my brain, then I could have like a couple of strokes and, Phineas Gage's little rod through my brain, and I'd be fine because, it's only a 10% chance of it hitting something useful. That's silly, but it's a little bit underscores how ridiculous this theory is. And I can't believe they made a movie based off of this. But it is true if we think about it from another perspective. The idea that only like 10% of your brain or so is actually neurons. And the other 90% are the accessory glial cells, sort of the behind-the-scene players that make, everything work, right? Like, you look at the new Top Gun movie and it's like Tom Cruise and Miles Teller or whatever, and it's, yeah, but you don't know of the hundreds of PAs and lighting people behind the scenes. So that's the glial cells, and we're going to take a look at them here. So neurons, everybody knows a neuron. We have our soma, or cell body. The axon hillock is the beginning of the axon. So the axon is like the cable that conducts the electrical signal through an action potential. It is wrapped in myelin. That myelin is created by oligodendrocytes in the CNS and Schwann cells in the PNS. There are little areas where it is not myelinated. These are the nodes of Ranvier. The action potentials jump between of nodes of Ranvier, and this quickens the conduction. And at the end, we're going to have these axon terminals, which are going to connect to other axon dendrites. And this is a synapse where neurotransmitters are released. So if we look then at an action potential, we're hovering around -70 as our threshold potential. A little bit of sodium leaks in, not enough. A little bit more sodium leaks in, not enough. A little bit more, not enough. A little bit more, we get to this threshold, this -55. Why is this the threshold? This is the voltage where sodium voltage-gated channels are open. Sodium floods into the cell, this depolarizes the cell around +40. Those voltage-gated sodium channels close, and the voltage-gated potassium channels open. Remember, we have a cell, and it is a salty banana, right? There's sodium on the outside, potassium on the inside. Potassium wants to go out, sodium wants to go in. So now the voltage-gated potassium channels open. They want to go out. So they start exiting. This depolarizes our cell again. This repolarizes our cell, bringing us down actually past -70 to -80, -90, which is a hyperpolarization. And the sodium-potassium ATPA is transported 3 sodium out for every 2 sodium in. It's going to bring us back to our resting state. Nissl bodies. These are rough endoplasmic reticulum fragments. Remember that the rough ER has a lot of ribosomes. Ribosomes have a lot of RNA. RNA is an acid, ribonucleic acid. Acids love bases, hence they are basophilic. They are going to bind with this is technically actually a positive stain. Too long, didn't read. If you wanted to stain just a cell body and not the axon, you would do a Nissl stain, because the Nissl bodies are not in the axons. They're just in the soma area. But additionally, there's more to this. If you get cellular damage, you're going to actually start to lose your Nissl bodies. And again, if the Nissl bodies are staining basophilic, staining blue, then you're going to get a red neuron phenomena. So you get these red neurons is a histological sign that we have ischemia and tissue damage. So a couple markers. So we have in our axons all of these microtubules, but we also have these neurofilaments. These are unique to axons, and so this is going to be a great stain. We also have stabilizing our vesicles with the neurotransmitters. We have a transmembrane protein, synaptophysin. All right, so moving on to astrocytes. Astrocytes, their analog is the satellite cell in the peripheral nervous system. They do like 3 main things. They wrap capillaries with tight junctions and foot processes. This helps maintain the blood-brain barrier. They maintain the neurotransmitter homeostasis, so they're going to provide the building blocks for new neurotransmitters, and they're going to eat up old neurotransmitters. And they are going to be important for a response to injury. Reactive gliosis, which we'll see in a second, friend or foe, it actually might have some downsides. And here's the foot process, and here we can be eating up all of the excess neurotransmitters, providing the building blocks. Here we're wrapping very tightly. I guess that's why I have the bread. I made this PowerPoint a while ago and never finished it. And I guess this is more recycling. Not 100% sure exactly what's the rhyme or reason of all of these pictures, but hopefully you guys get it. How can we stay an astrocyte and not, the rest of the cells? It's because astrocytes have GFAP, glial fibrillary, acidic protein, GFAP. It's only in glial cells. So the point 1, you should know that GFAP is in astrocytes. Point 2 is in a response to injury, we have something called reactive gliosis, where glial cells will hypertrophy, they become bigger, and hyperplasia, they're going to divide a lot. And we can see that by notice, we're standing here with GFAP, we see a little bit, and now we see way more after the injury. And this has some benefits and some downsides, and I don't know. I guess we'll say it's more bad than good. I'm not really an expert on it, but we'll say more bad than good. Ependymal cells in the choroid plexus of the ventricles. These are going to generate cerebrospinal fluid, and they have these little cilia so that they can kind of like wave their arms, and you can kind of see them like creating a current, helping sweep the cerebrospinal fluid through the ventricular system. Microglia, they're only micro. It's kind of funny because they're technically macrophages, right? So arose by any other name. Macrophages in bone are osteoclasts. Macrophages in liver are Kupffer cells. Langerhans cells in the skin, right? And so macrophages in the brain are all just microglia. So it's kind of funny that a macrophage is actually a microglia. I guess that's like a little bit of it suggests how large all the other cells are in the brain, because all the other glial cells are macroglia, and so these macrophages are only microglia, sort of as a contrast. If you have HIV, they can become like a harboring site for the virus, and you get these multinucleated giant cells, and they do what macrophages always do: they patrol, they eat up garbage, etc. Oligodendrocytes are going to wrap neurons. So Schwann cells are going to wrap one-to-one. Oligodendrocytes are going to wrap several. So one oligodendrocyte can wrap more than one neuron. You also progressively myelinate more and more axons as you get older and older and older. Multiple sclerosis is going to target these oligodendrocytes and the myelin in the brain. Contrast, we have Schwann cells. It's just like a one-to-one. So here's my Schwann cell, here's my neuron, and it kind of like hugs it really tightly, and then it hugs it tightly more and more and more and more and more and more and more. I thought of like those cute little squirrels from the King Arthur movie. If anything, though, maybe it'd be better to use like the python from like the Mowgli. Rudyard Kipling, Jungle Book. There we go. Yeah, it's more like the boa constrictor wrapping something up. So you can think of it as a cute, cuddly squirrel. A boa constrictor doesn't matter. It wraps it very, very tightly, one-to-one peripheral. Chromatolysis, really this is chromatolysis and other things. We have three things we're looking at. This is just for axonal injury and neuron injury. So three things will happen. Chromatolysis. So like I think like a chromosome, think DNA, RNA. What are we talking about? We're talking about the Nissl bodies. The Nissl bodies, these rough endoplasmic reticulum fragments that are hanging around the cell are going to start to break down. So the chromosome lysis. And they're going to break down. Potentially, though, if we just say chromatolysis, this is reversible, but up to a point. I think usually it leads to apoptosis. And again, at some point you lose all your Nissl bodies. Nissl bodies have RNA. RNA is basophilic, stains blue. And so if you don't have them, you will have a red neuron. So that's one thing, is we might kind of have our Nissl bodies get broken down over here and then eventually degraded if we go through apoptosis, if it's too severe. The nucleus is going to kind of move over to the periphery, usually goes even a little bit more over to the periphery. And the cell is going to swell. So a bunch of water is going to come in and cause this whole thing to swell. And then Wallerian degeneration just means that, so let's say that this was where the axon is broken. Everything upstream of this is probably going to be fine, and we're actually just going to build more axon. But everything downstream is going to be basically, this is the Wallerian degeneration is going to be broken down. So this is the macrophages coming in to gobble up all of this extra stuff. Nerves travel in packs. So this whole thing is a nerve, right? So the whole thing is a nerve. And let's start with the axon. Here's the boa constrictor / lovey-dovey squirrel that's wrapping it. This is now wrapped in endoneurium. So the Schwann cell is wrapped in endoneurium. This is our first of three. Now we have a bunch of these axons wrapped in Schwann cells, wrapped in endoneuriums. 1, 2, 3, 4. We have all of these together. All of these together constitutes a fascicle. I think fascism is the idea that like a bundle of rods, each rod together is strong, but like wrapped together, they're even stronger. And that's the idea behind fascism. But you actually have, that's like a structural nomenclature as a fascicle. So here we have a fascicle, a bundle of nerves. Wrapped around this fascicle here is the perineurium. So perineurium is going to be right there. And, now we'll have a little bit of fat, a little bit of vasculature. But again, we have a couple of fascicles together wrapped in what we call a nerve. And on the outside of this nerve is the epi as in outside of the nerve. All right, lots going on here. So we have fast adapting receptors and slow adapting receptors. So fast adapting is a type of receptor that it quickly reaches a homeostasis and becomes uninterested in whatever stimuli it's interacting with. That is useful because if there is the slightest movement, because it's adapted, if something moves, it'll have to that's a new signal for it to pick up on. So it's really good at picking up on the slightest movement. If you're playing the slap game with your sibling, right, where like you have your palms facing up and their palms are facing down, and you're trying to slap their hands, you want to have fast adapting receptors that quickly adapt so that you notice even the slightest change. Slow adapting receptors, or if you're holding something and part of your nerves are trying to get a sense of the size and shape and quality and texture, those would be slow adapting receptors. A deep receptor is deep in the skin, and it's going to have a large receptive field. So if you imagine something like your back, right? Think of our homunculus. Like there's not a lot of nerves dedicated to the back. There's a lot of nerves dedicated to the hand. So let's think about the back. You're not going to have a lot of nerves, so you got to kind of space out the territory. So you're going to have these really deep receptors, which have, so here's one nerve, and it goes all the way to all of this skin. So in other words, if you poke me right there, which is right there, or you poke me right there, which is right there, it's the same nerve that's picking up on both of them. So in other words, I actually can't differentiate one poke from one area versus a poke in the other area because you've got this one nerve which is overworked and covering way too much territory. So you won't be able to localize touch very well. So here I say more precise. That should be less precise. Then we're going to have superficial, which is, again, look at our homunculus, look at our hand. We've got tons of nerves, so we can have them a little bit closer to the surface so they just cover smaller territory. But that way I can differentiate this poke here from this poke, which is here, because these are both getting picked up by superficial nerves, which again is more precise. All right, let's put all this together. I think of you're going into the alphabet A, B, C, D, E, and not that far into the alphabet, not that deep. In other words, very superficial in the alphabet, we come across M. So M's are these superficial mechanoreceptor. Mechanoreceptor kind of for the dorsal column medial lemniscus. It might be more complicated, but that's how I always thought of it. So the M's are the superficial one. And then you think about, okay, well, who's first in the alphabet? M-E-I or M-E-R? M-E-I, that's first. So that is the fast one. And it is superficial because it's not that deep in the alphabet. This is a superficial fast receptor. These are going to be the fingertips. Now, we also have fingertip receptors that are going to be slow because, again, we might want to detect movement. We also might want to appreciate the shape of something that we're holding. And so this is going to be superficial and slow. So Pacinian and R, these are deeper into the alphabet. So these are going to be deep. So this would be like on your back. You're also going to have them in your hands, but let's just make it easy. Think of your back. And then again, we're kind of racing through the alphabet after this tiebreaker. P comes before R, so this is faster. We get to this faster than we got to the R. So this is a fast deep, and this is a deep slow. I actually think that's a pretty helpful way to go through it. We then have free nerve endings, which can be myelinated or unmyelinated. These can be superficial here. These can also be deep here. We have photoreceptors for vision, thermoreceptors, which can be free nerve endings. So this is going to be the spinothalamic tract. Chemoreceptors for taste, smell, aortic and carotid receptors for cranial nerves 9 and 10. I think we also have baroreceptors for this, but I could be wrong. Then we have the area postrema, the CTZ, for picking up toxins for emesis, and then receptors in the hypothalamus, and then we have nociceptors for pain. These are also free nerve endings, spinothalamic tract, and there's actually going to be a bunch of different types of like a mismatch of receptors that are all working for pain. So yeah, mechanoreceptors is going to kind of be the DCML, and the free nerve endings is going to be the spinothalamic tract. Embryology, there we go. Let's talk about it. So we have this notochord here, which is going to induce via Sonic the Hedgehog factor. So this mesoderm notoderm is going to induce this neural plate to start folding via Sonic the Hedgehog hormone. It starts folding, it starts folding, it starts folding, and we get two different things to emerge from this folding. We get the neural crest cell, which becomes the peripheral nervous system, and then we get the neural tube, which becomes the central nervous system progenitor cells. Note that for the neural crest cells, this is the peripheral nervous system, but it actually covers a couple of things that seem kind of random. Melanocytes, and I always remember this because I remember the substantia nigra It has neuromelanin. That's why it's substantia nigra, dark substance. It's black. The neuromelanin and melanin and melanocytes are very similar, and so that reminds me that melanocytes are derivatives of the peripheral nervous system. And then the adrenal medulla. Well, we have catecholamines, like serotonin and stuff, and the Rafe nucleus, and a lot of epinephrine and norepinephrine in the sympathetic nervous system. So we also have a bunch of this in the adrenal medulla. So it's making neurotransmitters, which we typically find in the nervous system. So that reminds me as well that this is a peripheral nervous system lineage. And then the microglia. Remember, the microglia are kind of the macrophages of the brain. Macrophages are made in the bone marrow, and bone marrow is mesoderm. That reminds me, this is mesoderm. Technically, though, these come from the yolk sac progenitors, but that's too complicated, so I don't remember it that way. All right, so if we're progressing here, we start with the prosencephalon, the mesencephalon, and the rhomboencephalon, and these are going to become the telencephalon, diencephalon, mesencephalon, metencephalon, and myelencephalon, which becomes, and we kind of went, most of this lectures, we went from the superior to the inferior, the cerebrum, which is the basal ganglia, parts of the limbic system, and the cerebral cortex, the eyes, the thalamus, hypothalamus, midbrain, pons, cerebellum, medulla oblongata, we're going down. Now, how do you remember this? Because that's kind of a lot. I just remember that everything is in alphabetical order except for these two, right? We have M and R. That works. Then we have D, M, MES, MET, and then MYEL. So it's all alphabetical order except for you just got to remember the prosencephalon. I remember maybe like a pro comes first, and then tele is, I don't know, television is on top of your dresser. We're ending with a whimper. That's a bad, dumb thing to say, but yeah. Television on top of your dresser. That'll stick, right? Okay, cool. I think that's the end of everything. Hopefully that was helpful. There's a whole nother lecture, but hopefully I have time to get through tomorrow. Really hope everyone's doing well. Good luck to everybody. All the best. Another one coming.